Our universe contains many worlds beyond the ones we know. These distant planets, called exoplanets, orbit stars throughout space, each with its own physical conditions. Some reach extremely high temperatures, some are completely frozen, and others have properties not found in our solar system. A journey to every exoplanet would involve travelling through many different types of environments. At each location, we would observe new skies, new atmospheric conditions, and new scientific possibilities. But are we alone? What exists beyond our solar system? And how far can human curiosity take us? TRES 2b, also called Kepler 1b or GSC 03549-02811b, is a planet outside our solar system that circles around the star known as GSC 03549-02811. This star is located about 750 light-years away from Earth. The planet became well known in the year 2011 when astronomers identified it as the darkest exoplanet ever found. It reflects less than 1% of the light that falls on it. To give a sense of how dark it is, TRES 2b reflects even less light than charcoal or coal dust, meaning that to the human eye its surface would look almost completely black. However, because it lies so close to its parent star, the planet still shines with a very high brightness in space, glowing not from reflection, but from the strong heat it receives. The measurements of its size and weight show that TRES 2b is a gas giant, much like Jupiter in our solar system. But unlike Jupiter, which is far away from the Sun, TRES 2b orbits extremely close to its host star. This makes it part of the group of exoplanets that astronomers call hot Jupiters, giant planets with very hot atmospheres caused by their tight orbits. This star system lies within the field of view of the Kepler Space Telescope, which later gave even more detailed observations, but long before Kepler, TRES 2b had already gained attention. The story of its discovery began on August 21, 2006, when astronomers working on the Transatlantic Exoplanet Survey, shortened as TRES, spotted the planet. They found it by watching the tiny dimming of its star whenever the planet passed directly in front of it, a method known as the transit method. The discovery was made using small telescopes, only about 10 centimeters wide, called Sleuth at the Palomar Observatory in California and PSST at the Lowell Observatory in Arizona. A few weeks later, on September 8, 2006, the finding was confirmed at the W.M. Keck Observatory in Hawaii, this time by measuring the star's radial velocity, which showed the slight pull caused by the planet. More work followed. In the year 2007, researchers improved the estimates for the planets and the star's properties. Then in the year 2008, another study showed something remarkable, that the TRES 2 system is actually a double star system. This discovery meant that astronomers had to revise their measurements, since having two stars instead of one changes the way the planet's orbit and its properties are understood. Later that same year, more exact observations showed that the orbit of TRES 2b is tilted by about -9 degrees, give or take 12 degrees, compared to the star's equator. The planet orbits in the same direction that the star spins, which is called a prograde orbit. In March 2009, NASA launched the Kepler spacecraft, a telescope built specifically to find new planets by the transit method. Just 1 month later, in April 2009, Kepler sent back its first images, known as its first light. Out of all the objects in its view, TRES 2b was chosen as one of only 2 examples to show in these first images. It was not the only exoplanet in the telescope's field of vision, but it was the only one clearly shown in that first release. This gave TRES 2b an important role as a kind of test planet, used to check the accuracy of the spacecraft's instruments. Kepler's observations added new layers of understanding. Astronomers were able to confirm the planet's mass not only through transit dips, but also by studying small changes in the brightness of its host star. These brightness changes came from several effects: the gravitational pull of TRES 2b slightly stretching the shape of the star, and tiny changes in light caused by Doppler beaming, a shift in brightness due to the motion of the star. Then came the most dramatic result. In the year 2011, data from Kepler showed that Tauri S2b has an amazingly low albedo, the scientific word for reflectivity. Its geometric albedo was measured at only about 0.04%, making it the darkest planet ever found. For comparison, Even coal or black acrylic paint reflects more light than TRISS 2b. Scientists guessed that its true albedo is less than 1%, far below what had been seen for any other planet. The reasons for this extreme darkness remain a puzzle. One idea is that TRISS 2b simply lacks the bright clouds that make Jupiter shine so brightly. Its closeness to the star heats the planet to such high temperatures that clouds of bright particles cannot form. Instead, its atmosphere may contain chemicals that strongly absorb light, such as vaporized sodium and potassium, or perhaps gaseous titanium oxide. However, some models rule out heavy compounds like oxides of titanium and vanadium, since it is unlikely they would stay in the upper atmosphere. More broadly, scientists note that hot Jupiters in general tend to be dark, since sodium and potassium strongly absorb visible light. The only major exception so far is another hot Jupiter called Kepler 7b, which has an unusually high reflectivity of around 38%, plus or minus 12%. TRISS 2b is also thought to be tidally locked to its star, meaning one side of the planet always faces the star in endless daylight, while the other side stays in endless night. In the year 2015, astronomers estimated that the temperature on the dark night side of the planet is still a burning 1,885 kelvins, with an uncertainty range of about plus 51 and minus 66 kelvins. To put that in simple terms, this is hotter than melted lava on Earth. Even after many years, TRISS 2b continues to interest astronomers. Its strange, light-absorbing atmosphere and its nearly completely black appearance make it one of the most mysterious planets ever studied. Each new observation sharpens the picture, but also deepens the puzzle of why this world is so dark. Proxima Centauri b is an exoplanet that orbits within the so-called habitable zone of the red dwarf star Proxima Centauri, located in the constellation of Centaurus. This planet is also called Proxima b or Alpha Centauri Cb. Its parent star, Proxima Centauri, is the closest star to our Sun. It lies at a distance of about 4.2 light-years, or about 1.3 parsecs from Earth, making it part of the well-known triple star system Alpha Centauri. Within this system, Proxima b and Proxima d, together with the argued candidate planet Proxima c, are the nearest exoplanets ever found outside our solar system. Proxima Centauri b travels around its star at a very close distance, only about 0.048 astronomical units, which is around 7,253,000 kilometers, or roughly 4,506,000 miles. The planet finishes one full orbit in just a little more than 11 Earth days. By comparison, Earth takes about 365 days to circle the Sun. As of the year 2025, scientists know only a small amount about the physical nature of Proxima Centauri b. Most proof shows that it is a rocky Earth-like planet. Its lowest estimated mass is about 1.06 times that of Earth, and it may also be slightly bigger in radius. However, whether or not the planet has an atmosphere is still unclear, and this part is key for knowing if it could support life. One of the problems is that Proxima Centauri is a flare star, often sending out strong bursts of radiation into space. Such bursts could blow away any atmosphere the planet might have, making habitability less likely. The finding of Proxima Centauri b was announced on the 24th of August in the year 2016 by the European Southern Observatory. The planet was confirmed after several years of Doppler spectroscopy studies of the star. Its finding was praised as a groundbreaking moment in planetary science and quickly drew worldwide attention to the Alpha Centauri system. By the year 2023, Proxima Centauri b had become the most widely known exoplanet to the general public, mainly because of its closeness to Earth, which raises hopes that one day robotic probes could be sent there. Long before its finding, astronomers had already looked at Proxima Centauri in their search for exoplanets. Early studies in the years 2008 and 2009 had ruled out the presence of very large planets in its habitable zone. Statistically, small planets are quite common around red dwarf stars. On average, each dwarf star is expected to host between 1 and 2 planets, and about 20 to 40% of red dwarfs may have planets lying in the habitable zone. This is especially important since red dwarfs are the most common type of stars in the whole galaxy. Before the year 2016, data from telescopes at the European Southern Observatory in Chile showed strange wobbles in Proxima Centauri's movement that could not be explained by normal stellar activity such as flares. This pointed to the presence of an orbiting planet. In January of that same year, a group of astronomers started the Pale Red Dot project with the goal of confirming this hidden world. On the 24th of August 2016, the team, led by Guillem Anglada Escudé, officially announced the finding of Proxima Centauri b. The Proxima system has shown more surprises since then. In the year 2022, astronomers confirmed the existence of another planet, Proxima Centauri d, which orbits even closer to the star. A third candidate, Proxima Centauri c, was reported in the year 2020, but its existence remains questioned, as the signals may have been caused by data mistakes. Some reports have also suggested a dusty belt of material around Proxima Centauri, but this too remains unproven. Proxima Centauri b is about 20 times closer to its star than Earth is to the Sun. Its orbit takes roughly 11.185 Earth days. As of the year 2021, astronomers are still unsure if its orbit is perfectly round or slightly stretched, but they believe the planet has little to no tilt in its spin. The age of Proxima Centauri b is unknown. Interestingly, Proxima Centauri itself may have been pulled into the Alpha Centauri system at some point in the past, which means it might not be the same age as the other two stars, Alpha Centauri A and Alpha Centauri b, both of which are about 5 billion years old. Because of its closeness to its star, Proxima Centauri b is very unlikely to have stable moons. By the year 2025, astronomers estimated the lowest mass of Proxima Centauri b to be about 1.055 Earth masses, with a margin of error of about 0.055. If the orbit is tilted at about 47 degrees to our line of sight, then the true mass would be closer to 1.44 Earth masses. That makes it very close to Earth in size, but the exact radius of the planet remains unclear. Depending on its makeup, it could be slightly smaller than Earth, or up to 40% bigger. Some models suggest it could be like Mercury, with a large metal core, while others picture it as a water-rich world. Measurements of the star's elemental makeup, mainly iron, silicon and magnesium, may later help scientists decide the likely makeup of the planet. Although little is directly known, computer simulations have been used to explore possible features of Proxima Centauri b. These models consider Earth-like geology, inner heating from radioactive decay, tidal heating from the star, magnetic fields, possible amounts of water or other easily changing substances, and how all of these parts might change over billions of years. Most scientists think the planet did not form where it is today. Instead, it likely formed farther away from the star, where more material was present, and later moved inward to its current close orbit. This movement would have strongly shaped its makeup. Depending on the materials involved, Proxima Centauri b could have ended up with a very dry surface, like Mercury, or with plenty of water and ices. Different formation ideas remain possible, many of which depend on whether other planets are present in the Proxima system. Scientists believe that Proxima Centauri b, the planet orbiting the small red star Proxima Centauri, may be tidally locked to its star. This means that, just like our moon always shows the same face to Earth, Proxima Centauri b might always keep one side facing its star. If that were the case, one side of the planet would be in endless daylight, while the other side would be stuck in permanent darkness. Such a situation would create very harsh conditions, with only certain areas between the hot side and the frozen side possibly able to support life. But researchers also point out that the planet might not actually be tidally locked. If the shape of its orbit is slightly stretched instead of perfectly round, that is, if its orbital eccentricity is greater than about 1/10, or even as low as 6/100ths, then the planet could enter into a different rhythm, something like the planet Mercury in our solar system. Mercury spins 3 times on its axis for every 2 orbits around the Sun. In a similar way, Proxima Centauri b might spin in a 3:2 resonance, or perhaps even follow other ratios such as 2:1. Interactions with other possible planets around Proxima Centauri, or even gravitational pushes from the nearby Alpha Centauri star system, could also increase its orbital eccentricity. If the planet is not a perfectly round sphere but instead has an uneven, stretched shape, then it could be caught into one of these non-locked spin states even with very little eccentricity. However, being in a non-locked orbit comes with its own problems. The constant stretching and squeezing of the planet by tidal forces would heat up its rocky inside, creating volcanic activity and possibly upsetting the dynamo effect that could make a protective magnetic field. How exactly this works depends heavily on the inner structure of the planet and how it reacts to this tidal heating over time. Now, let us look at the parent star itself, Proxima Centauri. This star is a red dwarf, which means it is a small, dim star that burns hydrogen very slowly compared to our Sun. Proxima Centauri shines with only about 0.005% of the visible light that our Sun gives off, and on average it produces about 1/6 of the Sun's total energy output. Proxima Centauri shines with only about 0.005% of the visible light that our Sun gives off, and on average it produces about 1/6 of the Sun's total energy output. Despite being such a weak star, Proxima Centauri b orbits very close to it, so it still gets around 70% of the infrared radiation that Earth gets from the Sun. But there is a downside. Proxima Centauri is what astronomers call a flare star. At times it can suddenly brighten 100 times within only a few hours. Its overall average brightness is measured at about 15.5% of the Sun's light output. In terms of size and mass, Proxima Centauri has only about 12.2% of the Sun's mass and about 15.4% of the Sun's radius. Its surface temperature is about 3050 Kelvin, which is much cooler than the Sun's roughly 6000 Kelvin. Proxima Centauri belongs to the spectral class M, more exactly an M 5.5V type, meaning it is still on the main sequence of stars, slowly fusing hydrogen at its core. Its magnetic field is also far stronger than the Sun's, reaching a strength of about 600 Gauss, and it cycles in strength roughly every 7 years. This star is the closest star to our Sun, which is why it is named Proxima, meaning nearest. It lies about 4.24 light-years away, which is roughly 1.3 parsecs. Proxima Centauri is part of a 3-star family, along with Alpha Centauri A and Alpha Centauri B, which orbit each other as a close binary pair. Over billions of years, the pull from these stars may have changed Proxima Centauri B's orbit, drawing it closer to its star. In the year 2012, astronomers thought they had found a planet around Alpha Centauri itself, but this claim later turned out to be unclear. Despite being so close to Earth compared to other stars, Proxima Centauri is too faint to be seen without a telescope, except perhaps during one of its extremely strong superflares. Proxima Centauri b lies in what astronomers call the classical habitable zone, the area around a star where liquid water could exist on the surface. The planet gets about 65% of the energy Earth gets from the Sun. Its estimated average surface temperature is about 234 Kelvin, which is roughly 39 degrees below 0 Celsius, or 38 degrees below 0 Fahrenheit. Whether this planet could actually support life depends on many things: the details of its orbit, the kind of light its star makes, and the behavior of any clouds or hazes that might form in its atmosphere. There are two main ideas for what kind of atmosphere Proxima Centauri b might have. One idea is that in its early history, its water condensed while its lighter hydrogen gas escaped into space, leaving behind an atmosphere rich in oxygen or carbon dioxide. Another idea is that the planet first formed farther from its star and later moved inward, keeping much of its water and maybe even some hydrogen. If Proxima Centauri b does have an atmosphere, it would likely contain gases like oxygen and carbon dioxide. Together with the star's strong magnetic activity, these gases could make colourful auroras in the planet's skies, perhaps even visible from Earth with powerful telescopes, but only if the planet has its own magnetic field. Scientists have used advanced climate models, the same kind used to study Earth's weather and long-term climate, to explore what conditions might exist on Proxima Centauri b. The results show many possible worlds. The planet could be completely frozen over, partly covered in ice, or it could have small or large oceans. It might even have a strange landscape with eyeball Earth patterns, where one side facing the star has a central ocean surrounded by ice, while the rest of the planet stays frozen. Another possibility is a lobster-shaped area of liquid water near the equator, with two branching areas of open ocean stretching out like claws. Some researchers also suggest that under a kilometre-thick layer of ice, Proxima Centauri b could hide a slushy, global underground ocean. A huge number of other things would shape its climate: the way heat moves through its atmosphere by convection, the presence of continents, which could help control carbon dioxide through the carbonate-silicate cycle, the bombardment of cosmic rays, which would be stronger here than on Earth, the movement of heat by oceans, which could spread warmth across the planet, the saltiness of those oceans, which would change how they behave, ozone chemistry, which could raise temperatures in the upper atmosphere and change the surface, the speed at which the planet rotates, which controls the making of atmospheric waves, the flow of internal heat, which could melt ice sheets from below, the movement of sea ice, which could either trap the planet in a global freeze or keep areas of ocean open. One of the biggest questions about whether life could exist on Proxima Centauri b is whether the planet can even keep an atmosphere. The steadiness of its atmosphere is uncertain, and many factors that change it are still unknown. To begin with, Proxima Centauri is a red dwarf star that hits its planet with huge amounts of high-energy radiation, especially ultraviolet light and strong X-rays. Proxima Centauri b receives between 10 and 60 times more of this harsh radiation than Earth does, especially in the form of X-rays. Scientists believe that in the far-off past the planet may have been hit with even more radiation, maybe around 7 to 16 times more total extreme ultraviolet and X-ray energy than Earth has ever received. This kind of radiation is dangerous to a planet's atmosphere. Hydrogen, which is the lightest of all gases, is very good at taking in this energy. Once heated, hydrogen atoms and molecules can move so fast that they escape the planet's gravity and drift into space. In the process, the radiation can also split water molecules into hydrogen and oxygen, with the hydrogen escaping while pulling oxygen and even nitrogen along with it. Over time, this means a planet can lose much of its water and atmosphere. Heavier gases like nitrogen and carbon dioxide can sometimes leak away on their own too, though this process is mostly slower and would not fully strip away an Earth-like atmosphere. But radiation is only one danger. Stellar winds and violent bursts of plasma called coronal mass ejections bring an even greater threat. The stellar wind from Proxima Centauri is thought to hit Proxima Centauri b with a force that could be between 4 and 80 times stronger than the solar wind that hits Earth. Even more worrying, the pressure of this wind may be about 10,000 times greater than the solar wind made by our Sun. The strong ultraviolet and X-ray radiation can swell the upper atmosphere of the planet so much that it stretches beyond its protective magnetic field, making it easier for the stellar wind to strip the gases away. Another problem is the magnetic cycle of Proxima Centauri itself. Unlike the Sun, which has an 11-year cycle, Proxima Centauri has a 7-year-long magnetic cycle. Depending on which stage of this cycle the star is in, the stellar wind near Proxima Centauri b may be 10 to as much as 1,000 times thicker than what Earth faces. As of the year 2018, scientists still do not know whether Proxima Centauri b even has a global magnetic field at all. It is possible that only the upper layers of its atmosphere make a magnetic field. If the planet does not have a strong inner magnetic field, the stellar wind could push deep into the atmosphere and peel away parts of it, a process that might change greatly from day to day, or even from year to year. There is also the issue of tidal locking. Because the planet is so close to its star, it may always keep the same side facing Proxima Centauri, much like the Moon always shows the same face to Earth. If that is the case, the side facing away from the star could become so cold that the atmosphere might freeze and fall there, especially if it is made mostly of carbon dioxide. In such a situation, frozen carbon dioxide could gather into glaciers, which might recycle and spread again, but this would still be a major challenge for habitability. Another point has to do with the history of the star itself. Unlike stars like our Sun, red dwarfs such as Proxima Centauri used to shine even more strongly during their early years, when they were still in the so-called pre-main sequence stage. Back then, the habitable zone, the area around the star where liquid water can exist, was farther away than it is now. This means that if Proxima Centauri b formed in its current orbit, it may have spent as much as 180 million years, much too close to its star for water to ever turn into liquid. During that time, the planet might have gone through a runaway greenhouse effect, with its water boiling into steam, being broken apart by ultraviolet light and losing its hydrogen into space. This is a fate similar to what scientists believe happened to the planet Venus in our own solar system. Adding to all this, violent asteroid impacts could also upset Proxima Centauri b's atmosphere, or even boil away any oceans that might exist there. On the other hand, there are also possible ways for the planet to recover. If Proxima Centauri b were covered in ice with an ocean hidden beneath, it might go through cryovolcanism, eruptions of water and ice instead of melted rock, at levels like the volcanic activity on Io, one of Jupiter's moons. This process could make a thin exosphere, like the faint atmosphere found on Jupiter's moon Europa. Even if Proxima Centauri b lost its first atmosphere long ago, volcanic activity could later rebuild a second one. Such a new atmosphere would likely hold large amounts of carbon dioxide, which is heavier and more steady than a nitrogen-rich, Earth-like atmosphere. If oceans are present, they could help balance and steady this second atmosphere, stopping it from falling apart. Also, if comets exist in the Proxima Centauri system, their icy impacts could bring fresh water to the planet over time, helping to return what was lost. Scientists believe that a young planet like Proxima Centauri b could get water in several different ways. Water might come through icy comets crashing into the planet, or through chemical reactions in the early atmosphere and surface. Yet, no one knows exactly how much water Proxima Centauri b actually got during its formation. A study by Rebus and his team in the year 2016 suggested that the planet may have lost no more than the same amount of water as one whole Earth ocean. Later studies, however, pointed to the chance that the losses could have been far greater. In fact, in the year 2017, Erapetian and colleagues said that the planet might lose its whole atmosphere in less than 10 million years. These guesses, though, depend strongly on how thick the atmosphere was to begin with, something that stays very uncertain. When astronomers talk about the habitability of a world, they usually mean one simple thing: can liquid water exist on the surface? For most meanings of life beyond Earth, liquid water and a protective atmosphere are needed. Of course, it is possible that life could hide below the surface, in underground oceans, like the ones suspected beneath the icy shell of Europa, one of Jupiter's moons in our solar system. But life like this would be very hard to find from light years away. Even so, scientists sometimes picture Proxima Centauri b as a frozen, ocean-covered world that might hide secret seas beneath its surface. The habitability of planets around red dwarfs like Proxima Centauri is one of the most hotly argued topics in astronomy. Several challenges stand in the way. Proxima Centauri itself is a very active star. Its flares and bursts of radiation, combined with the effect of tidal locking, which keeps one side of the planet always facing the star, could make it very hard for steady, life-friendly conditions to form. Unlike the harsher X-ray and extreme ultraviolet radiation, Proxima Centauri's ultraviolet light is somewhat redder and cooler. This means it acts less strongly with organic molecules and might make less protective ozone. Yet strangely, the star's violent outburst could strip away any ozone layer that does form, leaving the surface open to dangerous radiation. If the planet's orbit is not perfectly round, it might drift in and out of the habitable zone during its trip around the star, making the chance of steady conditions even harder. Certain gases such as oxygen and carbon monoxide might build up in the atmosphere to harmful levels. On the other hand, high oxygen could also make the rise of complex life more likely. If oceans exist, tides caused by the pull of the star could shape the environment. Coastlines might go through cycles of flooding and drying, starting chemical reactions that could help life begin. Tides might also help the rise of natural biological rhythms, similar to Earth's day and night cycles, and stir the oceans to mix nutrients, fueling the growth of marine organisms. Red dwarfs do have one advantage, however. They live far longer than stars like our Sun, lasting even longer than the current age of the universe. That means they could give life plenty of time to grow. But their light is not well suited for Earth-like photosynthesis that makes oxygen. Instead, it might only allow anoxygenic photosynthesis, a different process that does not release oxygen. Whether such life could be seen from Earth stays a mystery. One study in the year 2017 even said that the productivity of an ecosystem on Proxima Centauri b might be only about 1/5 of what Earth's ecosystems reach. As of the year 2021, no telescope has been able to directly take a picture of Proxima Centauri b. The planet orbits too close to its star, and from Earth's point of view, it does not seem to pass in front of the star. Careful searches for such transits have all come up empty. Still, scientists are listening closely. In April and May of the year 2019, the Breakthrough Listen project found a strange signal called BLC-1 that seemed to come from Proxima Centauri's direction. Hopes briefly rose that it might be a sign of alien technology, but later studies showed it was almost certainly a signal made by humans on Earth. Future tools, however, may change everything. Huge ground-based telescopes and strong space observatories, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, may one day separate the light of Proxima Centauri b from its star. If so, scientists could study whether the planet reflects starlight from an ocean, check the signs of gases in its air, and even look at how heat moves across its surface. Reaching Proxima Centauri b in person is another story. Even Voyager 2, one of the fastest spacecraft ever made by humans, would need about 75,000 years to get there. New ideas like ultra-thin solar sails that travel at 1/5 the speed of light have been suggested, but such spacecraft would face problems such as slowing down when they arrive, or surviving hits from tiny bits in the space between stars. One bold program, the Breakthrough Starshot project, aims to make this dream possible within the 21st century. If you were standing on Proxima Centauri b and looked up at the sky, the view would be amazing. The two bright stars of the Alpha Centauri pair would shine far more brightly than Venus does in our skies, with stunning brightness levels of -6.8 and -5.2. The Sun itself would appear as a modest star in the constellation of Cassiopeia, with a brightness similar to stars like Achernar or Procyon. The familiar constellations would look familiar yet different, with Sirius glowing near Betelgeuse, Procyon shining in Gemini, and our Sun shining faintly between Perseus and Cassiopeia. From Earth, scientists know where to look. In the southern constellation of Centaurus, on clear dark nights, they can point their telescopes toward the faint red glow of Proxima Centauri, the closest star to our solar system, hidden just beyond the reach of the naked eye. HD 189 733b is a fascinating exoplanet located in the small constellation called Vulpecula, which means the little fox. It is about 64.5 light-years away from our solar system, or nearly 20 parsecs in space measurement. This distance makes it one of the closest hot Jupiters known to scientists. The planet was first found on the 5th day of October in the year 2005 by a group of French astronomers. They spotted it by watching how the planet passed in front of its star, temporarily dimming the star's light, an event called a transit. Later, it was also confirmed using a method called Doppler spectroscopy, which measures the tiny wobbles in a star's motion caused by the pull of an orbiting planet. HD 189 733. B is a giant world, slightly bigger and heavier than Jupiter, the largest planet in our solar system. Its mass is about 16% more than Jupiter, and its size is about 11% larger. The planet races around its star at an amazing speed, more than 152 kilometers per second, which equals roughly 341,000 miles per hour. At that pace, it completes a full orbit in just over 2 days. Because it circles so close to its star, the planet is extremely hot and unlivable, falling into the group scientists call a hot Jupiter. Even with its harsh nature, HD 189 733b has become one of the most studied exoplanets in history. It was the very first exoplanet to have a heat map of its surface made, showing temperature differences between its day and night sides. It was also the first to have its colour measured, a bright cobalt blue, most likely caused by Rayleigh scattering in its atmosphere, the same effect that makes Earth's sky look blue. Scientists have also observed it in X-ray light, confirmed the presence of carbon dioxide in its skies, and even found signs of extreme weather, including winds so strong that they may drive molten glass rain sideways across the planet. On the 6th day of October, in the year 2005, another team of astronomers publicly announced their own detection of HD 189 733b. Then, in the year 2006, a group led by Drake Deming found strong heat emissions in the infrared, measured during a secondary eclipse, when the planet moves behind its star and its heat is briefly hidden. NASA's Spitzer Space Telescope later joined the study. On the 21st day of February in the year 2007, NASA showed that Spitzer had collected detailed spectra from HD 189 733b and another hot Jupiter, HD 209458b. These observations helped scientists understand the chemical makeup and heat patterns in the planet's atmosphere. In the year 2008, scientists tried to detect the planet's reflected light using a method called polarimetry. This would have been the first time visible light was directly observed from an exoplanet. By the year 2011, the same team improved their measurements and suggested that the planet reflects more blue light than red, again pointing to Rayleigh scattering. In the year 2013, the planet's deep blue colour was confirmed by another method, making HD 189 733b the first planet whose colour had been measured in 2 different ways. However, later studies using better polarimeters questioned these results, setting stricter limits on how much light the planet actually reflects. In January of the year 2008, astronomers made detailed spectral observations during a transit of the planet. These revealed important details about its atmosphere. If molecular hydrogen is present, it corresponds to a pressure of about 410 millibars, with some uncertainty of plus or minus 30 millibars. Models also suggest that tiny particles of magnesium silicate, the same mineral found in Earth's rocks, may form haze or clouds in its skies. The temperatures are extreme, ranging between about 1340 and 1540 kelvins, hotter than molten lava on Earth. In the visible spectrum, astronomers have also detected elements like sodium and potassium, using powerful instruments like the UV spectrograph on the European Southern Observatory's Very Large Telescope in Chile. These studies not only confirm the makeup of the atmosphere, but also give hints about its temperature and pressure. More recently, in the year 2024, scientists used the high-accuracy espresso spectrograph to improve our knowledge of HD 189 733b's atmosphere. They confirmed the presence of sodium and, for the very first time, detected lithium in its skies. They also noticed that the sodium signals were shifted in wavelength, a sign of fast and strong winds moving through the atmosphere. However, these measurements also revealed a challenge. The signals from the planet are often changed by the star itself due to its rotation, surface activity, and limb darkening. This effect, called planet-occulted line distortion, shows just how tricky and delicate studying exoplanet atmospheres really is. Together, all of these discoveries make HD 189 733b one of the most amazing exoplanets ever seen. Its close distance to Earth, blazing speed, bright blue colour, and stormy atmosphere have made it a true lab for understanding the strange and exotic worlds that exist beyond our solar system. In July of the year 2013, NASA announced something exciting. For the very first time, the scientists had seen a planet passing in front of its star while being studied in X-ray light. What they found was surprising. This planet's thick atmosphere blocks about 3 times as many X-rays as it does visible light. Earlier, in March of the year 2010, other observations using a special ultraviolet wavelength known as hydrogen Lyman alpha showed that the planet is actually losing its atmosphere into space. Its atmosphere is being stripped away at a huge rate, somewhere between 1 and 100 gigagrams of gas every second. Scientists discovered this because they saw a huge stretched cloud of hydrogen atoms, called an exosphere, around the planet. This made HD 189 733b only the second planet ever found, after HD 20958b to show clear signs of its atmosphere escaping into space. This alien world is also known for having one of the deepest transits ever measured in astronomy. When it crosses in front of its star, it blocks about 3% of the star's light, a very large amount for an exoplanet. The tilt of its orbit, called the longitude of the ascending node, is about 16 degrees away from the north-south direction in our sky, with a possible error of about 8 degrees. Along with HD 20958b, it was among the first 2 planets to be studied directly using spectroscopy, a method that lets scientists break apart the light and see what gases make up the atmosphere. Both planets orbit stars that are very bright compared to other exoplanet host stars, which is why they continue to get so much attention from scientists. Like most planets of this type, so-called hot Jupiters, HD 189 733b is thought to be tidally locked. This means one side of the planet always faces its star in constant daylight, while the other side stays in eternal night. Interestingly, the planet is not squashed or flattened in shape, nor does it have large moons bigger than about 80% of Earth's size. It also does not have the spectacular rings we see around Saturn. An international team led by Svetlana Berdugina of the Zurich University of Technology, using the 60-centimeter Swedish KVA telescope in Spain, managed to detect the faint glow of polarized light reflecting off the planet. This showed that the scattering atmosphere of HD 189 733b is at least 30% bigger than the solid body of the planet itself. At first, scientists thought the planet's atmosphere belonged to what they called the PL class, meaning it did not have a temperature inversion layer in its upper atmosphere. This would make it somewhat like very cool brown dwarfs, which also lack certain chemicals like titanium and vanadium oxides. Later observations tested this idea, but the results were not clear. However, scientists did find that high in the atmosphere, about 1,000 kilometers above the main body, there is a hazy layer that makes the sky look red at sunset. Early guesses also suggested that the atmosphere should have traces of sodium and potassium. At first, these were hidden behind the haze, but sodium was eventually found at 3 times the amount of sodium seen in HD 20,958b. Potassium was found much later, in the year 2020, though it was only in small amounts. HD 189 733b was also the first extrasolar planet where scientists confirmed the presence of carbon dioxide in its atmosphere. Even more recently, in the year 2024, hydrogen sulfide, a gas that smells strongly like rotten eggs, was also found in the planet's skies. Back in the year 2007, the Spitzer Space Telescope was used to carefully measure the planet's heat. Over 33 hours, astronomers watched the world complete half of its orbit. They found that temperatures range between about 973 kelvins, roughly 700 degrees Celsius, and 1,212 kelvins, close to 940 degrees Celsius. This showed that the planet's atmosphere spreads heat fairly evenly across its surface, although the hottest region was shifted about 30 degrees east of the point directly facing the star. This fit predictions from models of hot Jupiters, which suggest strong winds move heat from the day side to the night side. Scientists at the University of Warwick later found that winds on this planet reach incredible speeds, up to 8,700 kilometers per hour or 5,400 miles per hour, making them some of the fastest winds ever recorded on any planet. NASA even published the first ever brightness map of an exoplanet based on these temperature readings. On the 11th of July in the year 2007, a team led by Giovanna Tinetti announced that they had found strong signs of water vapor in the atmosphere of HD 189 733b. This was later confirmed by the Hubble Space Telescope, which also found neutral oxygen and methane, a chemical made by living things. Later still, the Very Large Telescope in Chile found carbon monoxide on the planet's day side. The discovery of methane was especially puzzling, since the extreme heat of the atmosphere, about 700 degrees Celsius, should normally cause methane and water to react, leaving only carbon monoxide. Nevertheless, in the year 2021, detailed studies confirmed that the atmosphere does indeed have a small but clear amount of water vapour, about 0.004% by volume. As the planet moves across the face of its star, it also produces what astronomers call the Rossiter-McLaughlin effect. This is seen as tiny shifts in the star's light spectrum, caused by the planet blocking different parts of the spinning star's surface. The strong gravitational pull of this heavy, close-orbiting planet makes its star wobble noticeably, with a semi-amplitude of about 205 meters per second. Measurements showed that the planet's orbit is well lined up with the star's equator, differing by less than 1 degree. This suggests the planet formed calmly within its original disk of gas and dust, rather than being violently disturbed by collisions with other planets. In 2008, astronomers thought the planet's orbit might trigger stronger flares from its star whenever it passed a certain point. By 2010, some teams even claimed to see regular X-ray flares linked to the planet's position. However, by 2019, after careful analysis using data from the Arecibo Observatory, the MOST satellite and other telescopes, scientists concluded that earlier claims had been exaggerated. The star simply does not show signs of strong flaring or active sunspot-like regions. In other words, there is no proof that the star and planet interact through magnetic forces. Over the years, astronomers have also looked for moons around HD 189 733b. A study in 2014 suggested there might be one, based on small changes in the planet's brightness. But this proposed moon would have been orbiting too far from the planet to be real. Later studies between 2019 and 2020 suggested possible volcanic moons, similar to Jupiter's moon Io, around HD 189 733b and other hot Jupiters. These ideas were based on finding sodium and potassium gases that might have come from such moons, but a follow-up study in 2022 found no real evidence of any moons at all. CoRoT 7b, which was first called CoRoT Exo 7b, is an exoplanet that goes around the star CoRoT 7 in the constellation known as Monoceros, the Unicorn. It lies about 489 light-years away from Earth, which is the same as about 150 parsecs. The planet was first found through light observations by the French-led CoRoT mission, and its discovery was officially reported in February of the year 2009. At that time, Corot 7b held a very special record. Until January of the year 2011, when Kepler-10b was announced, Corot 7b was the smallest exoplanet ever to have its width measured. It was measured at about 1.58 times larger than Earth's width, which makes its overall size about 3.95 times that of Earth. It also carried the honour of being the very first rocky Earth-like planet found outside our solar system, rather than a gas giant like Jupiter. One of the most unusual things about Corot 7b is its extremely short path around its star. It goes around its star in only about 20 hours, meaning that a year on Corot 7b lasts less than one single Earth day. By putting together data from two methods, the planet's width from its transit across the star and its mass from radial velocity measurements, scientists learned that the planet's density is about the same as Earth's. This means that Corot 7b is truly a rocky world, not a giant ball of gas. During these same observations, astronomers also found another planet in the system, named Corot 7c. This second world is a super-Earth, with a mass about 8.4 times greater than Earth's. It goes around its star once every 3.7 days at a distance of about 6.9 million kilometers, which is equal to about 0.046 astronomical units, or roughly 4.3 million miles. Corot 7b was found by watching its star for tiny drops in brightness. Each time the planet passed in front of the star from our point of view on Earth, the star's light dimmed a little. By measuring how much the light dropped and knowing the star's size, astronomers were able to figure out the size of the planet. The Corot spacecraft studied the star between October 15th of the year 2007 and March 3rd of the year 2008 in the observing field known as ELRA-01. During this time, the spacecraft recorded 153 transit signals, each lasting about 1.3 hours, with a brightness drop of about 3.4 times 10 to the power of -4. After about 40 days of data collection, the spacecraft's alarm mode found the signal of Corot 7b, which then led to more ground-based observations to confirm that the object was really a planet. The official news of Corot 7b came a year later, on February 3rd of the year 2009, at the Corot Symposium held in Paris. The discovery was then printed in a special issue of the journal Astronomy and Astrophysics, which was focused on results from the Corot mission. Follow-up observations with telescopes on Earth ruled out almost all chances that the signal was a false finding. Later, the HARP spectrograph was used to measure the planet's mass using the radial velocity method. However, the star itself is very active, which disturbed the measurements and made finding the true mass of the planet very hard. The first printed study by Queloz and colleagues guessed the planet's mass to be about 4.8 times that of Earth. This gave it a density of about 5.6 grams per cubic centimetre, with an uncertainty of plus or minus 1.3, which is very close to Earth's own density. The study also suggested that there was a second planet in the system, Corot 7c, with a 3.7-day path. Another study by Hatzers and colleagues, which used Fourier analysis, suggested that Corot 7b might actually be heavier, with a mass closer to 6.9 times Earth's. They also found possible signs of a third planet, Corot 7d, with a mass similar to Neptune's and a path of about 9 days. Other researchers pointed out possible problems in the data. Pont and colleagues argued that there were larger mistakes in the HARPS measurements than first thought, and guessed that Corot 7b's true mass might lie anywhere between 1 and 4 times Earth's. They also said that the radial velocity conformation of the planet was on shaky ground, with only about 1.2 sigma certainty. Later, Boisset and colleagues tried to separate the signals caused by the star's activity from those caused by the planet. Their results suggested a mass of about 5.7 Earth masses, but with very large uncertainty. The Corot team then printed a second paper, studying only those datasets where several measurements were taken on the same night to cut down stellar noise. From this method, they guessed a higher mass of about 7.42 Earth masses, which meant an average density of 10.4 grams per cubic centimetre, much denser than Earth and closer to the rocky planet Kepler-10b. Finally, Ferraz-Mello and colleagues used a better method and found that earlier studies had underestimated the signals. Their result gave Corot 7b a mass of about 8 Earth masses, supporting the idea that it is a rocky planet with a huge iron core, more like Mercury than Earth. An independent check came from NASA's Spitzer Space Telescope. Spitzer confirmed that Corot 7b truly crosses in front of its star, with the same amount of dimming seen at different types of light. This confirmation, separate from the noisy radial velocity data, gave scientists very high confidence that Corot 7b is indeed a real planet. Its exact mass is still somewhat uncertain, but scientists think it to be a little over 6 times the mass of Earth, with a margin of error of about 2/3 of an Earth mass. However, its size and path are much better understood thanks to careful observations from the Corot Space Telescope. This planet moves extremely close to its parent star. So close, in fact, that the distance is only 1/23 of the gap between the Sun and tiny Mercury. Because of this extreme closeness, it finishes one full trip around its star in just 20 hours, 29 minutes, and a little over 9 seconds. Its radius is measured to be about 1.5 times that of Earth. At the time it was found, Corot 7b held the record for having the shortest path of any known planet. Living under such intense conditions, the surface of Corot 7b is believed to be unimaginably hot, possibly covered by huge seas of glowing lava. The makeup and density of the planet, though not perfectly known, suggests that it is rocky, much like Earth. Some scientists have wondered if it could belong to a special group of planets that contain not only rock, but also a large amount of water, perhaps as much as 40% of their mass. Yet, because this planet formed so close to its burning star, it is more likely that most of its water and other easily lost materials boiled away long ago. It is very likely that Corot 7b's spin has become tidally locked, meaning one side of the planet is forever turned toward the star, while the other stays in never-ending darkness. This would create extreme differences between the blazing day side and the frozen night side. Some theories even suggest that Corot 7b might be what astronomers call a Chthonian planet, the leftover core of a gas giant like Neptune, stripped of its thick atmosphere by the star's strong radiation. Others disagree, noting that the system is fairly young, making it more likely that Corot 7b has always been a rocky planet. If its path is not perfectly round, the gravitational pull from its star and from nearby planets could twist and stretch it, creating strong volcanic activity similar to the eruptions seen on Jupiter's moon Io. Detailed studies of Corot 7b have shown just how extreme this planet truly is. Even with uncertainties in its exact mass, it appears Earth-like in makeup, though far too close to its star to hold on to a thick atmosphere. On its permanent day side, temperatures may rise as high as the wire of a glowing light bulb, hot enough to melt rock into oceans of lava. Because of this, scientists have suggested that Corot 7b could be the first known example of a new type of exoplanets, which they call lava ocean planets. Models suggest that if the planet has about 5 times the mass of Earth, its inside structure would include a mantle with moving rock currents and a small iron core no more than 15% of the planet's mass, that is, less than 1 Earth mass. The mantle near the surface would move more actively than the deeper layers, since greater pressure below makes the rock more slow and sticky. On the burning day side, where the planet's face is scorched by constant starlight, the crust itself likely melts and becomes part of the moving currents, forming a huge molten sea. On the freezing night side, a crust forms, though still filled with volcanic pools of lava bubbling up from below. Interestingly, the moving cells on the hot day side are thought to be larger than those on the cooler night side. Researchers also believe that Corot 7b probably has a solid iron core, but because of its structure, it is unlikely to make its own magnetic field. The extreme heat on the star-facing side of the planet means that most of its lighter substances have boiled away. Instead, its thin atmosphere is thought to be made of rock vapour. At a temperature of around 2,500 kelvins, that is, about 2,230 degrees Celsius or 4,040 degrees Fahrenheit, the pressure may reach only 1 pascal, far thinner than Earth's atmosphere. This vapour may contain sodium, oxygen, silicon monoxide, and small amounts of potassium and other metals. Minerals such as enstatite, corundum, spinel, wollastonite, silica, and iron oxide might thicken out of this vapour and fall like strange mineral rain onto the surface. Elements such as titanium and iron may drift to the cooler night side before thickening into minerals like perovskite and guiculite. Meanwhile, sodium, being more easily turned into vapour, would stay in the air longer and fill most of the thin atmosphere. Yet, when astronomers looked closely using highly sensitive tools to detect traces of sodium or calcium in the planet's outer layers, they found nothing. Even signs of volcanic gases expected from tidal heating were missing. This matches the idea that Corot 7b's atmosphere is not like that of Mercury or any planet we know, but instead is a clear, ghost-thin layer of rocky vapours. From all the evidence gathered so far, scientists conclude that Corot 7b is unlike any of the rocky planets in our solar system. It is an alien world, a blazing world of stone and fire forever locked in a struggle with the star it goes around so closely. Kelt. 9b is one of the most amazing exoplanets ever found, and it has become famous for being a place of extremes. It belongs to a group of planets called ultra-hot Jupiters, which are giant gas planets that orbit very close to their stars, becoming much hotter than anything we can imagine in our own solar system. What makes Kelt 9b truly incredible is not only its size and heat, but also the unusual type of star it orbits. The star it orbits is called Kelt 9, and it is about 670 light-years away from our planet Earth. To give a sense of size, a single light-year is the distance that light travels in 1 year, moving at almost 300,000 kilometers every second. That means the light we see from Kelt 9 today actually left that star nearly 700 years ago, long before telescopes existed on Earth. Even at this huge distance, astronomers were able to detect the planet using a special survey tool called the Kilodegree Extremely Little Telescope, or KELT for short. This instrument gave the star and its planet their name. The discovery of Kelt 9b was officially announced in the year 2016, making it one of the most exciting finds of that time. By June of the year 2017, scientists had already determined that it was the hottest exoplanet ever found. The star Kelt 9 itself is a very unusual star for a planet to orbit. Unlike our Sun, which is a G-type main sequence star, Kelt 9 is between the B and A star types. It is described as a late B-type or early A-type star, falling into a rare middle category sometimes labelled as B9.5 to A0. In simpler terms, this means the star is much bigger, brighter, and hotter than our Sun. In numbers, Kelt 9 is about 2 to 3 times bigger in size and 2 to 3 times heavier than the Sun. Its surface temperature is around 10,170 Kelvin, which is about 9,897 degrees Celsius, or roughly 17,846 degrees Fahrenheit. This heat is extremely high compared with stars that usually have planets. Before Kelt 9b was found, only a few A-type stars were known to have planets. Specifically, only 6 of these stars had confirmed planetary systems, and among them, the hottest was the star WASP-33. However, even WASP-33 is much cooler than Kelt 9, with a surface temperature of 7,430 Kelvin, which is about 7,157 degrees Celsius, or roughly 12,914 degrees Fahrenheit. No B-type stars were ever known to have planets before Kelt 9, which makes this discovery very important. The chance that Kelt 9 is the very first B-type star known to have a planet adds even more uniqueness to the system. The orbit of Kelt 9b is also remarkable. The planet moves around its star in a nearly circular path, but the orbit is tilted compared to the star's rotation. The distance between the planet and the star is incredibly small, only 0.03462 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, so this means Kelt 9b orbits its star at less than 1/20th of the distance between Mercury and the Sun in our own solar system. Because it is so close, the planet completes a full orbit in less than 1.5 Earth days. This is amazingly fast compared to Earth, which takes 365 days to circle the Sun. In size, Kelt 9b is a truly giant planet. It has a mass about 2.8 times bigger than Jupiter, which is the largest planet in our solar system. But even though it is so heavy, its radius is nearly twice that of Jupiter. This means the planet is puffed up, giving it a much lower density. In fact, its density is less than half of Jupiter's, which suggests that the extreme heat from the star is making its atmosphere expand. Like many hot Jupiters, Kelt 9b is tidally locked to its star. This means the same side of the planet always faces the star, while the other side is always in darkness. This creates a world where one side experiences endless scorching daylight, while the other side lies in permanent night. Such tidal locking is common for planets very close to their stars because strong gravity gradually slows the planet's rotation until it matches its orbit. The atmosphere of Kelt 9b is being lost very quickly. Because the planet is so close to such a hot star, it receives a strong blast of radiation. The outer layers of its atmosphere stretch almost to the edge of what is called its Roche lobe, the area around a planet where its gravity can hold material. Once the atmosphere reaches this limit, the gas can more easily escape into space. This means that Kelt 9b is losing its atmosphere very fast, basically evaporating under the strong radiation from its star. In the year 2020, scientists estimated this atmospheric loss, and it was very high, between 18 and 68 Earth masses for every billion years. If this rate continues, the planet could eventually lose much of its gas over long periods. As of the year 2022, the exact makeup of Kelt 9b's atmosphere is still unknown. However, scientists think it has a lower ratio of carbon to oxygen compared to other planets. This detail is important because the balance between carbon and oxygen affects what kinds of molecules form and how the atmosphere's chemistry works. Even though its chemical makeup is uncertain, one fact is clear. Kelt 9b is the hottest exoplanet ever seen. The day side of the planet reaches temperatures of about 4,600 Kelvin, which is roughly 4,327 degrees Celsius, or about 7,820 degrees Fahrenheit. To compare, this makes the planet's day side hotter than some small stars called K-type stars. The heat is so strong that molecules on the day side cannot stay together. Instead, they break apart into single atoms. This allows normally hidden elements, those that usually become solid or liquid on cooler planets, to exist freely as atoms. Among these are neutral oxygen, neutral and singly charged iron, and singly charged titanium. These atoms exist separately on the hot day side, but when moved by winds to the cooler night side, they recombine into molecules. This breaking apart and reforming process is indirectly confirmed by observations showing the planet is very good at moving heat from its day to night side. The efficiency is about 0.3, and scientists think this is mostly because energy is released and absorbed when hydrogen molecules break and then reform. Even more surprisingly, in the year 2021, astronomers studied the planet's atmosphere in detail and found clear evidence of metal oxides and metal hydrides, metals combined with oxygen and hydrogen. This was unexpected because scientists did not think these compounds could survive at such extreme heat. Later, when even higher resolution instruments were used, no molecular emissions were detected from the day side. This shows how hard it is to study a place as extreme as Kelt 9b, where conditions push the limits of what we understand. Another interesting feature of this planet is its thermosphere, the outermost layer of the atmosphere where temperatures rise sharply with height. For Kelt 9b, models suggest that the thermosphere can reach temperatures between 10,000 and 11,000 Kelvin. This equals about 9,727 to 10,727 degrees Celsius, or roughly 17,540 to 19,340 degrees Fahrenheit. These extreme temperatures are thought to be caused by heavy atoms like iron, absorbing large amounts of energy from the star's radiation. The story of Kelt 9b is not just about numbers. It also shows a turning point in how astronomers think about planetary systems. For many years, scientists believed that giant planets like Jupiter could not exist around stars as hot as Kelt 9, because the radiation would be too harsh for a planet to form or survive. Yet the discovery of Kelt 9b showed that nature can create planets even in the most extreme conditions. This forces us to rethink where planets can exist and how different planetary systems can be across the galaxy. The incredible heat of Kelt 9b truly stretches our understanding of how planetary atmospheres work. On Earth, and even on the gas giants in our own solar system, molecules stay stable under normal temperatures. But on Kelt 9b, the rules are entirely different. Elements that would usually be locked away inside solid rocks or buried deep in the atmosphere float freely in the form of hot gas. Mighty winds sweep these atoms across the planet, carrying them from one side to the other in a never-ending cycle of breaking apart and coming back together. In this way, Kelt 9b acts like a natural laboratory, letting scientists observe how atoms behave in conditions that are closer to the inside of a star than a planet. It is like watching the chemistry of fire on a massive planetary scale. It is equally fascinating to think about how fast Kelt 9b races through space. The planet completes a full orbit around its star in less than 1.5 Earth days, which means it is moving at astonishing speeds. To hold such a tight path, Celt 9b must travel much faster than Earth does, which averages about 30 kilometers every second as it orbits the Sun. The strong gravitational pull of its host star drags the planet into this dizzying whirl, yet its atmosphere somehow endures, leaving astronomers amazed at its resilience. Another remarkable point is the possible future of Celt 9b. At the current estimated pace of losing mass, the planet could shrink considerably over time. While a billion years may feel endless to us, in the life of a star it is just a short span. The star that Celt 9b orbits is much bigger than the Sun and will burn out far sooner, lasting only a few 100 million years more. This means the system as a whole is fleeting on cosmic timescales. Eventually, Celt 9b might be reduced to a rocky or metallic core, or it could even be swallowed entirely by its star. What truly makes Celt 9b captivating to both astronomers and the public is not just its extreme conditions, but the way it defies expectations. It is hotter than many stars, bigger than Jupiter, and orbits a star that no one imagined could host a planet. Its atmosphere is slowly leaking into space, yet the planet survives. Celt 9. B shows us that the universe can create worlds so extraordinary that they challenge everything we thought we knew, pushing science into new and thrilling directions with every discovery. TRAPPIST-1d is a small and intriguing exoplanet, weighing only about 40% as much as Earth. It orbits on the inner edge of the habitable zone of its host star, TRAPPIST-1, which is an ultra-cool dwarf star located 40.7 light-years away, or roughly 12.5 parsecs, in the constellation of Aquarius. Scientists first discovered signs of this planet using the transit method, which tracks tiny dips in a star's light when a planet passes in front of it. The initial announcement came in the year 2016, but it took several more years of observation and analysis to learn more about the planet's likely characteristics. Among the 7 known planets orbiting TRAPPIST, 1. TRAPPIST-1d is the second least massive. Despite being so small, the planet receives just a little more sunlight than Earth, about 4.3% more, placing it right on the inner edge of the star's habitable zone, where liquid water could potentially exist. Observations from the James Webb Space Telescope in the year 2025 suggested that TRAPPIST-1d may have no atmosphere at all. However, scientists note a small chance it could still have a thin atmosphere, though confirming this would require more advanced detection methods. Because TRAPPIST-1d was detected through the transit method, researchers could measure its radius very accurately. It's about 0.788 times the size of Earth, with only a small margin of error of around 70 kilometers. By studying the variations in its transit timing and running detailed computer simulations, scientists were also able to calculate the planet's mass, density, surface gravity, and general composition. Its mass is just 0.388 times that of Earth, making it one of the lightest exoplanets known. Early estimates suggested the planet's density was about 61.6% that of Earth, around 3.39 grams per cubic centimetre, with a surface gravity less than half of Earth's. This made TRAPPIST-1d much heavier than Mars, nearly 3 times Mars' mass, but initially thought to be less dense. Such a low density suggested the presence of a thick atmosphere or other volatile materials. Models indicated that most of the planet is rocky, but up to 5% of its mass could be made of a volatile layer, which might include an atmosphere, oceans, or ice. Later studies refined these numbers, showing the planet to be denser than previously thought, closer to 79.2% of Earth's density, or 4.35 grams per cubic centimetre. The planet's equilibrium temperature, the theoretical temperature based on the sunlight it receives, ranges depending on assumptions about its surface. If it had a perfectly dark surface that reflects no light, its temperature would be about 282.1 Kelvin, which is 9 degrees Celsius or 48.1 degrees Fahrenheit. With a reflectivity similar to Earth, its temperature would be around 258 Kelvin, which is about minus 15 degrees Celsius or 5 degrees Fahrenheit. These temperatures are surprisingly similar to Earth's average equilibrium temperature of 255 Kelvin or minus 18 degrees Celsius, which is about minus 1 degree Fahrenheit. TRAPPIST-1 deorbits extremely close to its star, completing one full orbit in just 4.05 Earth days, which is roughly 97 hours. The distance from its star is a mere 0.02, 228 astronomical units, or just over 2% of the distance between Earth and the Sun. For comparison, Mercury, the closest planet to our Sun, orbits in 88 days at about 0.38 astronomical units. Because of the small size of TRAPPIST-1 and the closeness of TRAPPIST-1D's orbit, the star appears about 5.5 times larger in the sky than our Sun does from Earth. Although a planet this close to our Sun would be scorched, the dimness of TRAPPIST-1 means that TRAPPIST-1D receives only slightly more sunlight than Earth, keeping it within the inner portion of the habitable zone. The host star, TRAPPIST-1, is an M-type ultracool dwarf with a mass of only 0.089 times the Sun's mass, placing it near the boundary between the smallest hydrogen-fusing stars and brown dwarfs. Its radius is about 0.121 times that of the Sun, and its surface temperature is relatively cool at 2,516 Kelvin, or 2,243 degrees Celsius, which is 4,069 degrees Fahrenheit. The star is estimated to be between 3 and 8 billion years old, while our Sun is about 4.6 billion years old. TRAPPIST-1 is unusually rich in metals, having about 109% of the Sun's metal content, which is unexpected for such a small star. Its luminosity is tiny, only 0.05% of the Sun's, meaning it emits very little visible light. Stars like TRAPPIST-1 can live extraordinarily long lives, up to 4 to 5 trillion years, which is hundreds of times longer than the Sun's remaining lifetime of about 5 billion years. Because of this longevity, TRAPPIST-1 may outlast most other stars in the universe, remaining when new star formation has stopped and older stars have died. From Earth, TRAPPIST-1 appears extremely faint, with an apparent magnitude of 18.8, far too dim to see without a telescope, as the naked eye limit is 6.5. Even from the close distance of TRAPPIST-1D, the star emits mostly invisible infrared light. The planet would receive less than 1% of the visible light Earth gets from the Sun, making daytime on TRAPPIST-1D never brighter than Earth's twilight. Still, the star would appear incredibly bright in the sky, shining at least 3,000 times brighter than the full moon does on Earth. In the year 2025, the remarkable James Webb Space Telescope turned its gaze toward the exoplanet TRAPPIST-1D. Using its powerful instruments, astronomers were able to study the planet's atmosphere, or the lack of one, with an unprecedented level of precision. Their analysis revealed, with more than 95% certainty, that thick, clear, cloud-free atmospheres could be ruled out. To put this in perspective, such an atmosphere would resemble a perfectly clear Venus, an early Mars, Titan, or the Earth during the Archean Eon. This left scientists with two main possibilities. The first and most likely scenario, which the researchers called the satisfactory fit for the data, is that TRAPPIST-1D has essentially no atmosphere at all, much like Mercury or the Moon. The second, far less likely option, the marginal possibility, is that the planet could have an atmosphere, but one cloaked in high-altitude clouds or aerosols that block starlight from passing through. In this case, any molecular signatures of gases would be extremely difficult to detect. Within this scenario, possibilities range from a very thin carbon dioxide atmosphere, reminiscent of Mars, to a Venus-like greenhouse world with high clouds, or even an Earth-like atmosphere if the effects of water clouds were considered. However, this clouded atmosphere scenario lies just at the very edge of what scientists call the 2 sigma boundary in statistical significance. This means it cannot be completely dismissed, but the current data do not strongly support it either. Lead scientist Piotr Goriev explained that the team's method, known as transmission spectroscopy, is only one way to look for atmospheres. While these results make the search for TRAPPIST-1D's atmosphere more challenging, she emphasized that they do not entirely close the door to the possibility that some kind of atmosphere could exist. Another factor that could explain the planet's atmospheric situation is its size. TRAPPIST-1D is only about 30% as massive as Earth. Like Venus and Mars, it might lack a protective magnetic field. Without this shield, the solar wind from its host star could strip away lighter, more volatile gases, such as water vapor, leaving behind a thin, hydrogen-poor atmosphere, similar to its smaller planetary neighbors in our own solar system. The story of TRAPPIST-1D's discovery began with a team of astronomers led by Michael Gillon from the Institut d'Astrophysique et Géophysique at the University of Liège in Belgium. Using the TRAPPIST telescope, which stands for Transiting Planets and Planetesimal Small Telescope, Located at the La Silla Observatory in the Atacama Desert of Chile, they carefully observed the dwarf star TRAPPIST-1, searching for signs of orbiting planets. By monitoring the star's light for tiny dips caused by transiting planets, a technique known as transit photometry, the team identified 3 planets roughly the size of Earth. They found that the 2 planets closest to the star are tidally locked, meaning the same side of each planet always faces the star, while the outermost planet seems to lie at the edge of the star's habitable zone, or perhaps just slightly beyond it. These observations were carried out between September and December of the year 2015, and the team published their groundbreaking findings in the May issue of the journal Nature in the year 2016. PSRB 162026b is an unusual exoplanet located roughly 12,400 light-years away from Earth in the constellation of Scorpius. Astronomers often call it by 2 well-known nicknames, Methuselah and the Genesis planet. These names are inspired by the biblical figure Methuselah, who was said to be the oldest person to have ever lived. The names fit perfectly, because this planet itself is unbelievably old. What makes this world even more special is that it goes around not just one star, but 2 stars at the same time. This type of path is called a circumbinary orbit. The 2 stars in question are very strange. One is a pulsar, known as PSRB 162026a, which is a dense spinning neutron star, and the other is a white dwarf, known as WDB 162026. This was the very first circumbinary planet ever confirmed, and it was also the first planet ever found inside a globular cluster. To this day, it remains one of the oldest known planets in the universe, with an age thought to be around 12.7 billion years. That is nearly 3 times as old as Earth. PSRB 162026b is a huge world, with a mass about 2.5 times greater than that of Jupiter. It goes around its stars at a distance of about 23 astronomical units, which is more than 3 billion kilometers away, a little farther out than Uranus is from the Sun. Because it is so far from its stars, each trip around them takes roughly 100 Earth years to finish. This whole system lies just outside the crowded centre of the globular cluster Messier 4. Since all the stars inside a globular cluster form at almost the same time, and since planets are born alongside their host stars, astronomers are sure that PSRB 162026b is also about 12.7 billion years old. By comparison, our Sun is only about 4.6 billion years old, making this planet truly old in space terms. The pulsar itself is amazing. It spins at an incredibly fast speed of about 100 times every single second. Despite its small size, likely only around 20 kilometers across, it holds more mass than our entire Sun, about 1.3 times the Sun's mass. Its surface temperature is thought to be as high as 300,000 Kelvin. The white dwarf partner is much smaller, with a mass only about 1/3 that of the Sun and a radius of about 1% of the Sun's size. Its surface temperature is estimated at around 25,200 Kelvin. These 2 stars go around each other at a distance of about 1 astronomical unit, finishing their shared orbit roughly every 6 months. With an age of between 12.7 and 13 billion years, this pair ranks among the oldest known double star systems. From Earth's point of view, the brightness of this double system is very faint. Its apparent magnitude is 24, making it far too dim to be seen without strong telescopes. The beginning of PSRB 162026b is still a puzzle. It is unlikely that the planet formed around the pulsar after its violent birth, because when a massive star collapses into a neutron star, it explodes as a supernova and loses most of its mass, a process that usually destroys or throws away nearby planets. Instead, scientists believe the planet was first made around the star that is now the white dwarf, and later this star, along with its planet, was caught into orbit around the pulsar during a close meeting in the crowded cluster. In our part of the Milky Way galaxy, such close star meetings are rare, but in thick globular clusters like Messier 4, they are fairly common. Astronomers think that around 10 billion years ago the neutron star caught the white dwarf's earlier star, while likely losing another star it had been going around with. Roughly 500 million years ago, that caught star began to swell into a red giant as part of its normal life cycle. As this happened, it began pouring gas and outer layers of matter onto the pulsar. This dramatic process spun the pulsar up to its current dizzying speed of just a few milliseconds per spin. For several 100 million years, the system shone as a low-mass X-ray binary, as the falling matter grew so hot that it glowed with high-energy X-rays. Eventually, the red giant used up its outer layers and shrank into the white dwarf we see today. Now the two stars go around each other calmly, with the planet going around both of them from far away. But the future of PSRB 162026b is not safe. The whole triple system is slowly moving toward the thick central area of Messier 4. In another billion years or so, it will likely pass close to another star. When that happens, the lightest member of the system, the planet itself, is expected to be thrown out. If so, PSRB 162026b will be sent drifting, leaving its cluster behind to wander forever through space as a lonely, starless planet. Like many of the planets found outside our solar system before the year 2008, the planet known as PSRB 1620-26b was first found through a clever method that astronomers often use when they cannot see a planet directly. Instead of spotting the planet itself, they look for tiny changes in the light or radiation coming from the star that the planet goes around. These changes, called Doppler shifts, are caused by the gravitational pull of the planet as it moves around its star. In this special case, the star in question was actually a pulsar, a kind of dead star that spins quickly and sends out beams of radiation like a space lighthouse. Astronomers noticed that the pulses from the pulsar seemed to change in rhythm, as though something was pulling on it. In the early 1990s, a group of astronomers led by Donald Backer was studying what they thought was a pair of stars locked together in orbit, a so-called double pulsar. But soon, their careful measurements told them something surprising. Two objects alone could not explain the strange changes they were seeing. A third object had to be there, pulling gently but clearly on the pulsar. Within just a few years, they were able to measure the gravitational effects of this hidden partner on the orbit of both the pulsar and its nearby white dwarf star. The measurements showed that this mysterious object was far too small to be another star. The only explanation was that it was a planet. In the year 1993, Stephen Thorset and his partners made the exciting announcement that the third object was indeed a planet. Studying the way the planet moved also let scientists learn more about the white dwarf star that shared the system. They could estimate its mass and, based on ideas of how such a planet might have formed, they suspected that the white dwarf should be fairly young and still very hot. On the 10th of July in the year 2003, a team of astronomers led by Stein Sigurdsson used the strong Hubble Space Telescope to finally see the white dwarf directly. Their findings confirmed the guesses. At a NASA press talk announcing the discovery, the planet was given the nickname Methuselah, after the biblical figure who was said to have lived longer than anyone else. This striking name caught the attention of the press and quickly spread around the world. In scientific circles, the planet is officially listed in the Simbad astronomical database as PSRB 1620-26b. However, some popular sources have at times called it PSRB 1620-26c, since it is technically the third member of its unusual triple system: the pulsar, the white dwarf, and the planet. But this label does not appear in official records, and it does not follow the modern rules for naming. Astronomers today use a system where stars are given uppercase letters and their planets lowercase letters. For example, Gliese 667 CC means the C planet going around the star Gliese 667c, which itself is the third star in a triple star system. By this rule, the right name for the planet is PSRB 1620-26b, since it goes around both the pulsar and the white dwarf. Still, outside scientific works, people continue to call the planet Methuselah. This informal name makes it feel more like the planets in our own solar system, which all carry mythological or historical names. In fact, Methuselah is the only planet known outside our solar system that has ever been given a biblical nickname. A few others, however, have received unofficial mythological or personal nicknames. For example, the planet called Dimidium, which was once nicknamed Bellerophon. The debated world Gliese 581g, sometimes called Zomina, or Zomina's world, after the wife of one of its discoverers, and the planet HD 209458b, which has sometimes been called Osiris. Janssen, also called 55 Cancri E, is one of the most interesting exoplanets discovered so far. It goes around a star named 55 Cancri A, which is very similar to our Sun. This planet is quite heavy for a rocky world. Its weight is about 8 times that of Earth, and its size is about twice as wide as Earth. The planet was officially found on the 30th of August in 2004. This was an important discovery because Janssen became the very first super-Earth found around a star that is still in the main part of its life, meaning a star still burning hydrogen in its core like the Sun. This discovery happened a whole year before another famous super-Earth, Gliese 876d, was found. Janssen is the closest planet to its star in its system, going around so fast that it completes one full orbit in less than 18 hours. At first, scientists thought it took about 2.8 days to go around the star, but better observations in 2010 showed the orbit was much shorter. Because it is so close to its star, Janssen is extremely hot. The side facing the star can reach over 3000 Kelvin, hot enough to melt many metals. Scientists noticed that the planet's heat changes over time, which could be a sign of active volcanoes. Some researchers even suggested that Janssen could be a carbon planet, mostly made of carbon-rich materials instead of the oxygen-rich rocks that make up Earth. The atmosphere of Janssen has been studied a lot. At first, astronomers thought it had hydrogen and helium, like Neptune or Jupiter. Later, observations did not support this. It seemed more likely that the atmosphere had heavier molecules, maybe a thin layer of vaporized rock. But in 2024, new measurements from the James Webb Space Telescope showed that Janssen has a thicker atmosphere with gases like carbon dioxide or carbon monoxide. In July 2014, the International Astronomical Union, IAU, started the Name Exoworlds project, letting the public choose names for certain exoplanets and stars. People could suggest names and vote. In December 2015, the IAU announced that 55 Cancri E would be called Janssen. The Royal Netherlands Association for Meteorology and Astronomy suggested this name to honour Zacharias Janssen, a Dutch spectacle maker often credited with helping to invent the telescope. Like many exoplanets discovered before NASA's Kepler mission, Janssen was first found using the radial velocity method. Astronomers studied the light from 55 Cancri A and measured tiny changes caused by the star's movement, pulled by its planet's gravity. At that time, 3 other planets were already known. After considering their effects, astronomers saw another signal with a period of about 2.8 days, suggesting a planet with at least 14 Earth masses very close to the star. The same data also confirmed another planet, 55 Cancri C. Janssen was one of the first exoplanets found with a mass similar to Neptune. It was announced at the same time as another hot Neptune, Gliese 436b, orbiting a red dwarf star. At first, some doubted Janssen's existence. In 2005, researcher Jack Wisdom rechecked the data and thought the 2.8-day orbit might be a mistake, suggesting instead a planet with a longer orbit of 260 days. Later, in 2008, Deborah Fisher's team confirmed both the 2.8-day planet and the 260-day planet. But in 2010, astronomers Sarah Dawson and Daniel Fabricki showed that the 2.8-day period was wrong, and Janssen's true orbit is less than a day, about 0.7365 days or around 18 hours. On the 27th of April in 2011, astronomers confirmed that Janssen passes in front of its star, causing a transit. This was observed after 2 weeks of nearly constant monitoring by the Canadian Space Telescope MOST. The transit matched the orbit predicted by Dawson and Fabricki. Transits like this are rare for bright stars and allow detailed study of the planet's size, density, and atmosphere. Janssen is extremely close to its star, at only 0.0154 astronomical units, much closer than Mercury is to the Sun. This tight orbit means the planet is likely tidally locked. One side, the day side, always faces the star and is blazing hot, while the night side is in permanent darkness. The planet's temperature is extreme. The day side reaches more than 2000 Kelvin, about 1700 degrees Celsius, or more than 3100 degrees Fahrenheit, hot enough to melt iron. Early observations with the Spitzer Space Telescope showed an average day-side temperature of about 2700 Kelvin, or 2430 degrees Celsius. The night side was cooler, around 1380 Kelvin, or 1110 degrees Celsius. A reanalysis in 2022 found even higher day-side temperatures, about 3,770 Kelvin, or 3,500 degrees Celsius, with a nightside limit of about 1,650 Kelvin. When Janssen was first found, scientists were unsure if it was a small gas planet like Neptune or a large rocky planet like Earth. The transit in 2011 allowed calculation of its density. Some thought it might be a water world, but no hydrogen was detected, suggesting its main gas could be carbon dioxide instead of water or hydrogen. Another idea is that Janssen is a carbon-rich rocky planet, unlike Earth's oxygen-rich rocks. If true, up to a third of the planet's mass could be carbon. Under high pressure and heat inside, some carbon might form diamonds, making Janssen a diamond planet. More studies are needed to confirm this. Scientists think a mix of forces, tidal forces from the star and orbital forces, could trap a hydrogen-rich atmosphere on the dark side. If the atmosphere is mostly gases from volcanoes mixed with hydrogen, the heavier gases stay near the planet, while lighter hydrogen drifts to the day side, where the star's X-rays and ultraviolet light destroy it. For this to work, Janssen would have had to become tidally locked early, before losing all hydrogen. This fits with some observations detecting hydrogen and other studies that did not see hydrogen being destroyed quickly. In February 2016, NASA reported that the Hubble Space Telescope detected hydrogen cyanide in Janssen's atmosphere, but no water. This suggested the atmosphere was mostly hydrogen or helium, and marked the first successful study of a super-Earth's atmosphere. In November 2017, the Spitzer Space Telescope observed Janssen in infrared light. It suggested a global ocean of molten rock under an atmosphere slightly denser than Earth's, possibly containing nitrogen and even oxygen, producing the unusual infrared signals. However, these results were not fully consistent with earlier findings. A study in 2012 did not detect escaping hydrogen, and another in 2020 did not detect helium. This means Janssen may no longer have its original hydrogen or helium atmosphere, but it could still have heavier gases like nitrogen or oxygen. In May 2024, astronomers used the James Webb Space Telescope to study Janssen more closely. Using its near-infrared camera and mid-infrared instrument, they measured the planet's heat in the range of 4 to 12 micrometers. These measurements showed that Janssen is not just a lava world with a thin rock vapor atmosphere, but has a real thick atmosphere rich in gases like carbon dioxide or carbon monoxide, possibly replenished by its magma ocean. Other observations show large swings in surface temperature, likely caused by volcanic eruptions sending dust into the air. This dust traps heat and blocks radiation from escaping. By 2022, astronomers also saw changes in the depth of the planet's transits, possibly caused by huge volcanic events or a ring-shaped gas cloud moving with the planet. Because Janssen is so close to its star, less than 1/10 of an astronomical unit, some scientists wondered if it could trigger flares on the star through magnetic interactions. In 2011, astronomers searched for radio signals from the star's outer layer but found none, leaving the question open. HAT P7b, which is also called Kepler 2b, is one of the most amazing planets ever found outside our solar system. It belongs to the group of worlds we call exoplanets, planets that do not go around our sun, but instead move around faraway stars many light years away. This interesting world was first found in the year 2008, and since then it has become one of the most studied and talked about planets outside our solar system. From the moment it was discovered, astronomers realized that it was not just another faraway planet, but something much more unusual, extreme, and even a little mysterious. The first thing that makes HAT P7b special is how close it travels to its star. Unlike Earth, which goes around the Sun at a safe distance of about 150 million kilometers, HAT P7b is very close to its star, moving so fast that its whole year lasts just over 2 days. Because of this closeness, it is hit with huge amounts of heat and energy from its star, much more than any planet in our solar system gets. As a result, this giant world is not only bigger and heavier than Jupiter, the largest planet in our own solar system, but it is also extremely hot, with weather so intense that it is hard to imagine. Scientists have tried to figure out how hot this strange world must be, and their results are amazing. On the side of the planet that always faces its star, called the day side, temperatures are thought to reach between 2630 and 2880 Kelvin. If we change these numbers into more familiar measurements, that is about 4,270 to 4,720 degrees Fahrenheit, or about 2,360 to 2,610 degrees Celsius, these fiery temperatures are hot enough to melt metals like iron or nickel, and much hotter than the surface of Venus, the hottest planet in our solar system. But HAT P7b does not cool down much even on the night side. On the half of the planet that faces away from the star, temperatures are still between 2211 and 2238 Kelvin. That is about 3,520 to 3,569 degrees Fahrenheit, or about 1,938 to 1,965 degrees Celsius. In other words, no matter where you go on this strange world, it would feel like being inside a giant burning oven that never really cools. But the extreme heat is just the start of this planet's strange story. HAT P7b has another feature that makes it even weirder. It is one of the darkest planets ever seen. Scientists measure how much light a planet reflects with something called albedo. An albedo of 1 means that an object reflects all of the light that hits it, like a perfect mirror, while an albedo of 0 means it reflects nothing at all, like a pitch-black surface. Earth, for example, reflects about 30% of the sunlight that hits it, giving it an albedo of about 0.3. HAT P7b, by contrast, reflects less than 3% of the light it gets. That means more than 97% of the starlight that hits it is absorbed by its atmosphere or surface. Imagine a giant, burning, super hot ball of gas that, even though it is extremely hot, looks almost black like coal when seen from space. This makes HAT P7b feel even more strange and mysterious. Finding this unusual world was not easy. It started with the HATNet project, a large program that set up telescopes in different parts of the world to look for planets passing in front of their stars. The project used several robotic tools, including HAT7, which was at the Smithsonian Astrophysical Observatory's Fred Lawrence Whipple Observatory in Arizona, and HAT8, which was on the roof of the Smithsonian Astrophysical Observatory's submillimeter array building on top of the volcano Mauna Kea in Hawaii. These telescopes, night after night, looked at the sky and took thousands of pictures to find tiny drops in starlight that could mean a planet had passed in front of a star. Between late May and early August of the year 2004, these telescopes focused on a patch of sky called HATNet Field G154. In this area, they watched about 33,000 stars almost every night. From their careful work, they collected a huge 5,140 pictures. After studying these images, astronomers noticed something remarkable. One star, named GSC 03547-01402, seemed to dim in brightness at very regular times. Each time its light dropped by about 7 millimagnitudes, a small but noticeable change, and the pattern repeated every 2.2047 days. Each dimming lasted about 4.1 hours, which strongly suggested that a planet was passing in front of the star, blocking a tiny part of its light as it moved. This star was later officially named HAT P7, with the P showing it was part of the planets discovered by the HATNet program. The discovery was even more reliable because of a lucky coincidence. The star HAT P7 was in an overlapping area between two fields watched by different HATNet telescopes, called G154 and G155. This meant the star could be watched independently, lowering the chance of mistakes. The HAT6 telescope in Arizona and the HAT9 telescope in Hawaii confirmed the transit by watching the nearby field G155. From late July 2004 to late September 2005, they gathered another 11,480 pictures. Together with the earlier data, this made a huge total of 16,620 data points, enough to confirm that a planet was indeed orbiting this faraway star. Soon after, another big step forward came from space. The star HAT P7 and its new planet were in the very first view of the famous Kepler mission spacecraft. This satellite was made to look for planets by watching stars for long times and measuring tiny changes in their brightness. When Kepler focused on HAT P7, it confirmed the planet with a certainty and detail that ground telescopes could never match. Kepler not only measured the planet's orbit more accurately, but also saw what happened when the planet went behind its star. These observations showed that HAT P7b had an atmosphere that absorbed light strongly and did not move heat well from the day side to the night side. In other words, the planet's skies kept the heat on the side facing the star, leaving the dark side still hot but somewhat cooler. Kepler's work on HAT P7b also showed that its instruments could detect planets much smaller than gas giants, even Earth-like planets in habitable zones. As time went on, HAT P7b continued to fascinate astronomers. On the 4th of July in the year 2011, this amazing world became part of history when the Hubble Space Telescope made its 1 millionth scientific observation by studying it. This milestone alone shows how important HAT P7b has been in increasing our knowledge of distant worlds. But the surprises did not stop. In August of the year 2009, scientists said that HAT P7b might have something very unusual: a backward orbit. Usually planets orbit their stars in the same direction the star spins, like the planets in our solar system orbit in the same direction the Sun rotates. A backward orbit, by contrast, means the planet moves around the star in the opposite direction of the star's spin. To find this, astronomers use the Rossiter-McLaughlin effect, which measures tiny changes in starlight as a planet passes across the spinning star. Their results suggested that HAT P7b was not only orbiting close to its star, but was going against the normal flow. This news came just one day after the first backward orbit was found in another planet, WASP-17b. Later studies, including one in the year 2012, confirmed it further. They measured the angle of the orbit compared to the star's spin, and found it to be about 155 degrees, with a possible error of 37 degrees. Such a tilted and reversed orbit is rare and shows that this planet has had a chaotic and violent past. Astronomers think that HAT P7b may not have always been where it is now. It probably formed much farther from its star, possibly about 3 times the distance between Earth and the Sun. But gravity from other objects in the system seems to have pulled it inward over time. The star HAT P7 has at least 2 other stars nearby. One of them, HAT P7c, is a small red star that orbits the main star, HAT P7a, at about 32 times the Earth-Sun distance. Its path is very stretched, moving in a long oval. The other star, HAT P7b, is much farther, at about 700 times the Earth-Sun distance. Astronomers think the far star may have caused a Kozai mechanism, a process where the gravity of a distant object changes the orbit of an inner companion. This chain of gravitational events could have pushed HAT P7b into a more stretched orbit, until tidal forces eventually made it more circular, locking it into its current, dangerously close backward path. In January of the year 2010, another discovery about HAT P7b made the news. For the first time, scientists noticed something called ellipsoidal light changes from this planet. This happens when a very large planet's gravity pulls on its star so strongly that it changes the star's shape. Instead of being a perfect round ball, the star gets stretched, more like an oval. As the star spins, its brightness changes a little, and scientists can measure these changes. Seeing this effect around HAT P7b not only taught us more about the system, but also showed how strong the gravitational pull is between the star and its close orbiting planet. Years later, in December of the year 2016, a group of scientists led by Dr. David Armstrong published an important letter in the journal Nature Astronomy. They shared evidence that HAT P7b has very strong winds that change speed a lot over time. These winds are believed to circle the planet, moving the brightest part of its atmosphere by large amounts. What is especially interesting is how fast these changes happen, sometimes in just a few tens of days, sometimes over hundreds. This suggested that the planet's global wind patterns and clouds are not stable, but very changeable. Models of the atmosphere even suggest that on the night side, strange types of rain might fall. Instead of water, the atmosphere could have drops or crystals of aluminum oxide, a mineral called corundum. On Earth, this mineral forms precious stones like rubies and sapphires. So imagine a world where clouds are not made of water, but of minerals that on Earth we would treasure as gemstones. In the skies of HAT P7b, storms of shining crystals could sweep across the night, creating one of the most amazing and deadly alien weather systems imaginable. All of these discoveries show a planet that is as extreme as it is fascinating. HAT P7b is bigger and heavier than Jupiter, hotter than any furnace we can imagine, darker than charcoal even with its high heat, and full of wild weather and strange clouds that rain gemstones. It orbits its star backward, as if breaking the normal rules, and it probably moved inward from a much farther orbit in a cosmic dance influenced by other stars. Studying it has marked many important milestones in astronomy, from being one of the first big successes of the Kepler mission, to being the target of the Hubble Space Telescope's millionth observation, to showing new ways we can study exoplanets through light changes and shifting atmospheres. In a universe full of billions of stars and planets, HAT P7b reminds us just how different and surprising other worlds can be. If we once thought planets were only like those in our own solar system, this distant giant proved that wrong. Instead, it shows that nature can make worlds so strange they seem like science fiction. Yet, thanks to the hard work of astronomers and the amazing tools they have built, we know HAT P7b is real. And as our technology gets better, it will not only keep revealing its secrets but also help us understand many other strange and wonderful planets orbiting faraway stars. Beta Pictoris b is a fascinating planet that exists outside of our solar system, a type of world astronomers refer to as an exoplanet. This extraordinary celestial object orbits a young and energetic star named Beta Pictoris, which is a relatively rare kind of star called an A-type main sequence star. Stars of this type are hotter and more massive than our Sun, shining brightly in blue-white hues. Beta Pictoris itself is situated roughly 63 light-years from Earth, which can also be expressed as approximately 19.4 parsecs, or a staggering 600 trillion kilometers. This star can be found in the southern sky within the constellation known as Pictor, which is Latin for the painter, and it is visible to the naked eye under good observing conditions due to its apparent brightness. Beta Pictoris b is classified as a super-Jupiter, which means that it is a gas giant planet that is significantly larger and more massive than Jupiter, the largest planet in our solar system. Estimates of its mass suggest that it weighs somewhere between 9 and 13 times the mass of Jupiter, with some precise measurements in recent years indicating it might be around 11 times Jupiter's mass, plus or minus 2. In terms of size, this planet is also impressive, with a radius approximately 46% larger than that of Jupiter. This makes it not only massive but also extraordinarily voluminous compared to familiar planets in our solar system. Its size and mass together suggest a planet with a very strong gravitational field and the potential to influence its surroundings in a significant way. The orbit of Beta Pictoris b around its parent star is quite remarkable. It follows a nearly circular path at a distance of roughly 9 astronomical units, or AU, from the star, which is almost 3.5 times the distance at which its sibling planet Beta Pictoris c travels. For context, 1 astronomical unit is the distance between the Earth and the Sun, roughly 150 million kilometers, so this planet is orbiting at a distance comparable to that of Saturn in our solar system. The orbital period, which is the time it takes to complete 1 full revolution around the star, is estimated to be about 20 to 21 Earth years, which makes it a slow traveller compared to planets in our inner solar system. Interestingly, its orbit lies almost exactly in the same plane as the dust and debris disk surrounding Beta Pictoris, suggesting a strong alignment with the disk from which it likely formed. Measurements show that its orbital eccentricity, or how stretched out its orbit is very low, meaning that its path around the star is close to being a perfect circle. The atmosphere and temperature of Beta Pictoris b provide another layer of intrigue. This super-Jupiter has a temperature estimated to be around 1724 Kelvin, which converts to approximately 1451 degrees Celsius, or 2644 degrees Fahrenheit. This is incredibly hot, especially considering that Jupiter itself is much cooler, with an atmospheric temperature of around 120 Kelvin at its cloud tops. The intense heat of Beta Pictoris b is thought to be the result of its massive size and the presence of thick clouds or dust in its atmosphere, which trap heat efficiently. The atmosphere, which has been studied in detail, appears to be heavily clouded or dusty, resembling in some ways the atmospheres of young brown dwarfs, rather than the relatively calm and clear atmospheres seen in older giant planets like Jupiter and Saturn. Studies have estimated the surface gravity of the planet to be lower than that of older giant planets, consistent with its relatively young age, as it has not yet fully contracted to its final size. One of the unique aspects of Beta Pictoris b is the precision with which astronomers have been able to measure its mass and orbital effects on its host star. In 2018, a landmark study directly detected the subtle motion of Beta Pictoris caused by the gravitational pull of this massive planet, an effect known as astrometric perturbation. This method of measurement was one of the first instances where an exoplanet's mass was determined by directly observing how it tugged on its star, rather than relying solely on indirect methods like radial velocity or transit data. The findings suggested that the planet's mass is about 11 times that of Jupiter, within a margin of error of 2 Jupiter masses. The star around which Beta Pictoris b orbits is itself an object of great interest. Beta Pictoris has a mass of approximately 1.75 times the mass of the Sun and a radius around 1.8 times that of the Sun. It is a young star, only about 12 million years old, making it a mere infant in stellar terms, especially when compared to our middle-aged Sun, which is roughly 4.6 billion years old. The surface temperature of Beta Pictoris is calculated to be 8,056 Kelvin, considerably hotter than the Sun's surface temperature of 5,778 Kelvin. It is also slightly richer in metals than the Sun, with a metallicity roughly 112% that of our star, which can influence the formation of planets and dust in its surrounding disk. Its brightness, or luminosity, is measured at about 8.7 times the luminosity of the Sun, indicating a star that shines with considerable intensity. From Earth, its apparent magnitude is 3, which is bright enough for observers to see it without any telescopic aid. The orbit of Beta Pictoris b is closely aligned with the rotation of its star and the orientation of the surrounding debris disk. Recent studies have measured the alignment, finding only a small deviation of about 3 degrees, with an uncertainty of plus or minus 5 degrees as of the year 2020. This alignment suggests that the planet formed within the disk and has not been significantly perturbed by other gravitational forces over its relatively short lifespan. The planet's rotation adds another layer of fascination. In 2014, astronomers managed to measure the rotation period of Beta Pictoris b for the first time for an extrasolar planet. By examining the broadening of carbon monoxide absorption lines in the planet's infrared spectrum, they calculated that it spins on its axis extremely rapidly, completing one full rotation in roughly 8.1 hours. This is faster than the rotation of Jupiter, which takes about 10 hours to rotate once. Subsequent refinements to the measurement suggested a rotation period of 8.7 hours, plus or minus 0.8 hours, confirming its status as one of the fastest spinning exoplanets known. The discovery history of Beta Pictoris b is itself a story of patience and technological advancement. The planet was officially announced on the 18th of November in the year 2008 by a team of astronomers led by Anne-Marie Lagrange. They used the NACO instrument, a sophisticated camera equipped with adaptive optics, mounted on the Very Large Telescope, which is located at Cerro Paranal in northern Chile. Interestingly, the initial images that eventually revealed the planet were taken back in the year 2003, but at the time, the data did not immediately reveal the presence of the planet. It was only after the images were reprocessed in 2008 using modern image processing techniques that astronomers identified the faint point of light as a planet. Follow-up observations in late 2009 and early 2010 confirmed its presence, observing it on the opposite side of the star, and these results were published in the prestigious journal Science. This discovery marked a milestone in astronomy, representing one of the closest orbiting planets ever directly imaged around its star. The orbit of Beta Pictoris b has been studied extensively, and detailed measurements suggest that it is nearly edge-on when viewed from Earth, with an inclination angle of approximately 88.5 degrees. Its orbital plane is slightly tilted, by roughly 3.5 to 4 degrees, relative to the main debris disk in the Beta Pictoris system. This small tilt indicates that the planet may be aligned with the inner warped section of the disk, providing insight into the dynamic processes occurring in young planetary systems. The planet's atmosphere and spectral characteristics have been examined in detail. In July of the year 2013, astronomers published the first study of its spectral energy distribution, analysing the light emitted and reflected by the planet across multiple wavelengths. They observed the planet in wavelengths of 1.265, 1.66, 2.18, 3.8, 4.05, and 4.78 micrometers, revealing evidence for a very dusty or cloudy atmosphere. These observations suggested that the planet resembles early L-type brown dwarfs in its atmospheric properties, but has lower surface gravity due to its younger age and ongoing contraction. Further studies, including a September 2013 analysis using data from the Gemini Observatory, refined these observations. They found that the planet emitted more radiation in the mid-infrared at 3.1 micrometers than expected from simple models, indicating the presence of small dust particles and thick clouds that trap heat and obscure deeper atmospheric layers. Temperature estimates from these studies suggest an effective temperature ranging from 1600 to 1700 Kelvin, with surface gravity estimates expressed as log G around 3.8 to 4.0. These fits imply a planetary radius between 1.46 and 1.65 times that of Jupiter, suggesting the planet may have formed slightly later than its host star and could be younger than the surrounding stellar environment. In 2015, astronomers created a short time-lapse video from direct images captured by the Gemini Planet Imager, showing Beta Pictoris b slowly orbiting its parent star over roughly 2 Earth years. This visual record allows scientists to study the planet's movement and interactions with the debris disk in a dynamic way. There is also speculation that Beta Pictoris b could have been responsible for a transit-like event observed back in 1981, which could indicate complex interactions within the system over decades. Later, in 2018, the PicSat CubeSat was launched with the goal of imaging the planet as it passed in front of its host star, further demonstrating the ongoing interest in this remarkable system. As of 2022, a combination of observational methods, including radial velocity measurements, astrometry, and direct imaging, has allowed astronomers to measure the mass and orbital characteristics of Beta Pictoris b with greater precision. These studies suggest a mass of about 11.7 times that of Jupiter, a semi-major axis, which is the average distance from the star of approximately 10 astronomical units and an orbital period of roughly 23.6 Earth years. Simulations and observational data have also indicated that the planet's rotational axis, or obliquity, could be misaligned. The degree of this tilt may depend on the planet's rotation speed, with faster spins implying a higher likelihood of misalignment. Potential causes for such obliquity include rare collisions with other planets, although this is considered unlikely, or gravitational interactions influenced by the presence of a large exomoon. A hypothetical exomoon with a mass comparable to that of Neptune, orbiting at a distance between 0.02 and 0.05 astronomical units, equivalent to roughly 20 to 50 times the planet's radius, over a period of 3 to 7 weeks could induce substantial tilts in the planet's spin axis, possibly reaching angles up to 60 degrees. Future observations, particularly those planned with the James Webb Space Telescope, aim to measure the obliquity of Beta Pictoris b, a feat that has not yet been accomplished for any extrasolar multiplanetary system. Detecting a non-zero obliquity could provide evidence for the presence of an exomoon, offering a rare glimpse into the dynamics of planetary systems beyond our own. Currently, a zero obliquity appears to be unlikely, which opens fascinating possibilities for the structure and history of the system. Pollux b, which has been formally given the name Thestius, is a fascinating and mysterious candidate for a planet beyond our solar system, known as an exoplanet. This celestial body, if it indeed exists, is thought to revolve around the bright star Pollux, which lies about 34 light-years away from our Sun, in the well-known constellation called Gemini, also popularly known as the Twins. Gemini is one of the constellations visible from Earth and has captivated stargazers for centuries due to its bright stars and mythological associations. Pollux itself is the brighter of the 2 main stars in Gemini and has been a focus of attention for astronomers exploring the possibility of planets orbiting stars beyond our own solar neighbourhood. In scientific literature, this potential planet is also often referred to as Beta Geminorum b, using the Latinized form of the star's name, or simply abbreviated as VGEM-b. Another less commonly used designation for the same object is HD 6209b, following cataloguing conventions in astronomy. The story of Pollux b is a tale of both promise and uncertainty. Based on the observations and calculations conducted so far, if this planet does exist, it is an enormous world, estimated to have a minimum mass roughly twice that of Jupiter, the largest planet in our own solar system. This immense mass alone places Pollux b among the most massive types of planets known, typically categorized as gas giants, meaning it is composed mostly of hydrogen and helium, rather than rocky material like Earth or Mars. Its orbit around Pollux is nearly circular, with the planet travelling around its host star at a distance of approximately 1.64 times the distance between the Earth and the Sun, a distance that astronomers refer to as astronomical units, abbreviated AU. Completing one full revolution around Pollux takes about 1 year and 6 months, or 1.61 Earth years. The orbital path of Pollux b, being so close to a circular shape, suggests a relatively stable gravitational relationship with its star, unlike highly elliptical orbits seen in some other exoplanetary systems. However, the very existence of Pollux b has not gone unchallenged. The scientific story surrounding this exoplanet is layered with debates, studies, and observations that alternately support and question its presence. The first announcement of its discovery came in the year 2006 when the astronomer RTP Hatzes, along with several collaborators, published their findings. They had employed a technique known as the radial velocity method, one of the primary ways astronomers detect exoplanets. This method involves careful measurement of subtle shifts in a star's light spectrum, caused by the gravitational pull of an orbiting planet tugging on the star and causing it to move slightly back and forth along our line of sight. These minute wobbles produce changes in the light emitted by the star, which can be detected and interpreted as evidence of a planet. The use of this method in the case of Pollux suggested the presence of a substantial planetary companion, sparking excitement and curiosity in the astronomical community. Interestingly, RTP Hatzes had first suggested the possibility of a planet orbiting Pollux as early as the year 1993. At that time, however, he expressed caution, noting that the observed wobbles or variations in Pollux's light might have been caused not by a planet, but by intrinsic variability within the star itself. Stars, especially evolved ones like Pollux, can display surface activity, pulsations, or magnetic phenomena that mimic the subtle effects a planet would have on the star's motion. As a result, the initial hypothesis of a planet was treated with skepticism as astronomers sought further confirmation and evidence. Following the announcement in 2006, several independent studies sought to confirm the existence of Pollux b. An early study published shortly after the discovery paper generally supported the notion of a planetary companion, but also emphasized some lingering uncertainty. The researchers acknowledged that while a planet was a strong explanation for the observed radial velocity variations, alternative possibilities could not be completely ruled out. Specifically, they suggested that intrinsic stellar behavior might still account for some or all of the observed signals. Another study conducted in the year 2008 independently analysed the data and found results that reinforced the idea of Pollux b as a planet, further strengthening the case for its existence. Yet the debate was far from settled. Subsequent research began to introduce more questions and doubts regarding the planetary hypothesis. A study in the year 2013, followed by a more detailed analysis in the year 2021, raised the possibility that the observed effects might instead be related to the star's own properties. In 2009, astronomers detected a weak magnetic field on Pollux. This discovery opened up the possibility that variations in the star's magnetism, rather than the presence of a planet, could be responsible for the changes in its radial velocity. Supporting this idea, measurements of Pollux's rotation period suggested that it might be similar to the orbital period attributed to Pollux b. Specifically, the 2021 study monitored Pollux for over 4 years, roughly 4.25 Earth years, and determined that the star rotates approximately once every 660 days, plus or minus 15 days. This is intriguingly close to the orbital period ascribed to Pollux b, which is about 590 Earth days. Although the two periods are not identical, the proximity raises the possibility of systematic errors in measuring the star's rotation or in interpreting the data. Therefore, astronomers remain cautious and continue to debate whether the signals attributed to a planet might instead arise from stellar activity or other non-planetary phenomena. Despite these scientific uncertainties, Pollux b has captured the public imagination, in part because of its official naming by the International Astronomical Union, often abbreviated as IAU. In July of the year 2014, the IAU launched a global initiative called Name ExoWorlds, designed to give formal names to certain exoplanets and their host stars. This process was not limited to astronomers. It actively involved the public, allowing people from around the world to submit nominations and vote for their preferred names. Through this democratic and educational initiative, individuals and groups had the opportunity to connect with the broader field of astronomy and contribute to the naming of distant worlds. The naming of Pollux B concluded in December of the year 2015, when the IAU officially announced that the winning name for the planet was Thestius. This name was based on a submission originally put forward by an organisation called the Skynet in Australia, who had suggested the name Leda, the mythological mother of Pollux in Greek and Roman mythology. However, the name Leda was already in use for other celestial bodies, including an asteroid and one of Jupiter's moons. To avoid duplication and confusion, the IAU decided to honour the original idea while modifying the name slightly, choosing Thestius instead. Thestius is derived from the name of Leda's father, Thestius, and thus retains the mythological connection while establishing a unique identity for this exoplanet. The tale of Pollux B, or Thestius, therefore intertwines the rigour of scientific inquiry with the creativity of human culture and myth. It highlights how astronomy is not only a pursuit of distant worlds and physical measurements, but also a human endeavour steeped in storytelling, tradition and imagination. Observational techniques, such as the radial velocity method, provide a precise and empirical approach to detecting planets many light years away, revealing subtle clues about the motion of stars and the possible presence of massive companions. At the same time, uncertainties in the data remind us of the challenges inherent in studying distant stars, where magnetic fields, surface activity, and other stellar phenomena can mimic planetary signatures. Furthermore, the narrative of Pollux B demonstrates the evolution of scientific ideas over time. The initial hypothesis in the year 1993, the formal discovery announcement in 2006, subsequent supporting studies in 2008, and later questioning studies in 2013 and 2021, together show the dynamic and self-correcting nature of science. Each observation, measurement and analysis contributes to a growing body of knowledge, refining our understanding of the universe while leaving room for curiosity, debate, and further investigation. In addition, the public naming process conducted by the IAU illustrates how science can engage broader audiences and foster global participation. By connecting exoplanets with human culture, mythology, and history, initiatives like Name ExoWorlds transform abstract celestial bodies into stories that resonate with people around the world, bridging the gap between empirical research and collective imagination. Thestius is no longer just a candidate planet orbiting a distant star. It carries with it a story of mythological heritage, international collaboration, and the quest to understand worlds beyond our own. Ceti is an intriguing exoplanet classified as a super-Earth, a type of planet larger than our Earth but smaller than the gas giants like Neptune or Jupiter. This planet circles a star similar to our Sun, known as a G-type star. Ceti itself is about 3.93 times the mass of Earth, and orbits its star once every 1.7 Earth years, travelling at a distance of approximately 1.334 astronomical units, almost 1 1/3 times the distance between the Earth and our Sun. The discovery of this planet was officially announced in the year 2017. The star around which Ceti revolves is a solitary star located in the constellation of Cetus, sometimes referred to as the Sea Monster. This star shares many similarities with our Sun in terms of its composition and appearance, but is somewhat smaller, having only about 78% of the Sun's mass. At a distance of just under 12 light-years, or roughly 3.7 parsecs from our solar system, Ceti is relatively close by in cosmic terms, making it the nearest single G-type star to the Sun. Ceti appears quite stable when observed from Earth. Its light output does not vary much, which indicates low stellar activity, and it is also relatively poor in elements heavier than hydrogen and helium, meaning it is metal deficient compared to our Sun. Despite this, it shines bright enough to be seen with the naked eye, having an apparent magnitude of 3.5. From the viewpoint of someone on Ceti, our Sun would be visible in the northern sky, appearing in the constellation of Bootes with a brightness of about magnitude 2.6. One fascinating feature of Ceti is the massive amount of dust surrounding it. Observations indicate that the star's surrounding disk contains more than 10 times the amount of dust present in our own solar system. This dense debris could pose challenges for the potential habitability of any planets orbiting Ceti, as it would likely lead to frequent impacts from comets and asteroids, far more so than Earth experiences today. Despite this hazard, astronomers remain deeply interested in the star due to its stability, sun-like characteristics, and proximity. These factors make Tau Ceti a prime target in the search for extraterrestrial intelligence, often abbreviated as Ceti, as it represents one of the most promising nearby systems where life might exist. Astronomers have carefully tracked the motion of Tau Ceti across the sky, a property known as its proper motion. Proper motion measures how fast a star moves relative to more distant background stars. Tau Ceti moves at a rate of 1.9 arcseconds per year, which translates to 1,900 years per degree across the sky, a speed considered high for stars. High proper motion often indicates that a star is close to the Sun, and in Tau Ceti's case, its measurements confirm a distance of about 11.9 light-years, placing it among the closest stellar systems to our own. It is the next closest star of its spectral type, class G, after Alpha Centauri A. Another aspect of Tau Ceti's motion is its radial velocity, which measures how fast it moves toward or away from the Sun. Using the Doppler effect, astronomers study the star's spectrum and notice slight shifts in absorption lines. A red shift indicates movement away from Earth, while a blue shift shows it is approaching. Tau Ceti has a radial velocity of roughly -17 kilometers per second, the negative sign showing that it is moving toward our solar system. Based on these measurements, the star is expected to reach its closest approach to the Sun in about 43,000 years, coming as near as 10.6 light-years, or roughly 3.25 parsecs. Combining the star's proper motion, radial velocity and distance allows astronomers to calculate Tau Ceti's movement through the Milky Way. Its speed relative to the Sun is about 37.2 kilometers per second. From this, researchers can estimate the star's orbit around the galaxy, finding that it has an average distance of 9.7 kiloparsecs, or about 32,000 light-years, from the center of the Milky Way, with an orbital eccentricity of 0.22, meaning its path around the galaxy is slightly elliptical rather than a perfect circle. The Tau Ceti system appears to contain only one main star. A faint optical companion has been observed with a magnitude of 13.1 and was measured to be 137 arcseconds from the primary star in the year 2000. While it might be gravitationally connected to Tau Ceti, it is considered more likely that it is simply a chance alignment from our perspective on Earth. Much of what is known about Tau Ceti comes from detailed spectroscopic studies. By analysing the light from the star and comparing it to theoretical models of stellar evolution, astronomers can estimate the star's age, mass, size, and brightness. Modern techniques, such as astronomical interferometry, allow direct measurements of the star's radius with remarkable precision, accurate to about 0.5%. Using these methods, Tau Ceti's radius has been determined to be approximately 79.3%, plus or minus 0.4% of the Sun's radius, roughly the size expected for a star slightly smaller than our Sun. The rotation of Tau Ceti has also been carefully studied. Astronomers monitor subtle periodic changes in absorption lines caused by singly ionized calcium, which trace magnetic activity on the star's surface. These observations indicate that Tau Ceti completes a full rotation roughly every 34 Earth days. The rotation also affects the width of spectral lines due to the Doppler effect. Light from the side of the star moving away from us is shifted to longer wavelengths, and light from the side moving toward us is shifted to shorter wavelengths. Analysis of these line widths gives the star's equatorial rotational speed multiplied by the sine of the tilt angle as about 1 kilometer per second. For comparison, a typical star of Tau Ceti's type would rotate at about 2.5 kilometers per second. This relatively slow rotation suggests that we might be viewing the star nearly pole-on, looking almost directly down on its axis of rotation. In a more recent study conducted in the year 2023, astronomers estimated that Tau Ceti, the nearby Sun-like star, completes one full rotation roughly every 46 days, with an uncertainty of plus or minus 4 days. The measured equatorial velocity multiplied by the sine of the inclination angle, often written as vec sin e, was about 0.1 kilometers per second, with an uncertainty of plus or minus 0.1 kilometers per second. These measurements suggest that we are viewing the star almost directly from above its pole, with an inclination angle of approximately 7 degrees, plus or minus 7 degrees. The chemical makeup of a star offers important clues about its history and development, including how old it might be. Stars form from clouds of dust and gas in space. known as the interstellar medium, which is mainly made of hydrogen and helium, with tiny amounts of heavier elements. Over time, as nearby stars live out their lives and die, they release heavier elements back into space, enriching the interstellar medium. This means that younger stars tend to have more of these heavy elements in their atmospheres than older stars do. Astronomers call these heavier elements metals, and the proportion of metals in a star is known as its metallicity. Metallicity is often measured by comparing the amount of iron, which is easy to detect, to the amount of hydrogen in the star. This ratio is then expressed logarithmically in comparison to the Sun's composition. Tau Ceti has a relatively low iron content compared to the Sun, indicating that it is almost certainly older. Earlier studies estimated its age at about 5.8 billion years, but more recent research suggests that it may be closer to 9 billion years old. By comparison, the Sun is approximately 4.57 billion years old. Depending on the method and model used to calculate it, estimates for Tau Ceti's age can vary widely, from as little as 4.4 billion years to as much as 12 billion years. In addition to rotation, another factor that can affect the width of spectral lines in a star's light is pressure broadening. This occurs because nearby particles influence the radiation emitted by individual atoms or molecules. The width of these lines depends on the pressure at the star's surface, which is itself determined by the star's temperature and surface gravity. Using this method, scientists have determined that Tau Ceti's surface gravity, expressed as log g, is about 4.4, very similar to the Sun's log g of 4.44. Tau Ceti shines with only about 55% of the Sun's brightness. For a planet to receive a similar amount of light and warmth as Earth receives from the Sun, it would need to orbit Tau Ceti at a distance of roughly 0.7 astronomical units, which is approximately the same distance as Venus is from our Sun. The star's chromosphere, the layer just above the visible surface of the star, currently shows very little magnetic activity, suggesting that Tau Ceti is quite stable. A 9-year observational study that looked at the star's temperature, surface granulation, and chromospheric activity found no systematic changes over time. Observations of calcium emissions in the H and K infrared bands hinted at a possible 11-year cycle, similar to the Sun's activity cycle, but it is much weaker. Some scientists have even suggested that Tau Ceti might currently be in a period of low activity similar to the historical Maunder minimum, which on the Sun coincided with a time in Europe known as the Little Ice Age, when sunspots were exceedingly rare. Spectral lines from Tau Ceti are extremely narrow, indicating low turbulence and slow rotation. The star's natural oscillations, studied through astroseismology, have amplitudes about half that of the Sun, and the oscillation modes do not last as long. Tau Ceti has captured the attention of astronomers for many reasons. It is relatively close to Earth, has characteristics similar to the Sun, and may host planets that could support life. Researchers often classify stars based on how similar they are to the Sun. A solar-like star is a general term, while a solar analogue is more restrictive, and a solar twin is an even closer match. Tau Ceti falls into the solar analogue category because it has a similar mass and relatively low variability, although it contains fewer metals than the Sun. Its sun-like traits have inspired both scientific studies and popular culture references for decades. In 1988, astronomers using radial velocity measurements found no evidence for massive planets orbiting Tau Ceti, at distances similar to that of Jupiter from the Sun. Over the years, increasingly precise measurements have continued to rule out such planets, at least until December 19, 2012. By then, the precision of velocity measurements reached about 11 meters per second, recorded over a period of 5 years. This effectively ruled out the presence of hot Jupiters, large gas giants very close to the star, and likely excluded any planets with a minimum mass equal to or greater than Jupiter and orbital periods shorter than 15 years. The Hubble Space Telescope's Wide Field and Planetary Camera conducted a survey of nearby stars in 1999, searching for faint companions to Tau Ceti, but none were found within the telescope's detection limits. These observations, however, could only rule out large brown dwarfs or giant planets close to the star. Smaller, Earth-sized planets in wider orbits remained possible. The absence of hot Jupiters is considered favourable because such massive planets, if they existed close to the star, could disrupt the habitable zone where life-friendly conditions might exist.